You have never seen Andromeda, not really. You've seen a faint smudge in the night sky, a polite blur through a telescope, maybe a photograph that fits neatly inside your screen. But if your eyes could register the full extent of what is actually there, Andromeda would stretch 6 times wider than the full moon across the darkness above you. A structure 220,000 light-years from edge to edge, a trillion stars bound into a single rotating disk. And it is coming toward us at more than 100 kilometers every second. This is not a distant neighbor. This is not a postcard from across the cosmos. This is a collision already in motion. And Andromeda is only one member of a family we have barely begun to map, the local group. More than 80 galaxies scattered across 10 million light-years of space, each one a different answer to the same question. What does gravity do when it has billions of years and an ocean of dark matter to work with? Grand spirals like Triangulum, still blazing with new stars. Smooth ellipticals stripped of their gas and left to fade. Lenticulars caught somewhere in between, neither alive nor dead. Chaotic irregulars that never learnt the rules, and dwarf spheroidals so faint, so dominated by invisible mass, they are barely galaxies at all. They are not randomly scattered. They are falling toward a center of gravity that is not the Milky Way, and not Andromeda either. Because scale in the universe is not about how far away something is. It is about what happens to your sense of size the moment you stop seeing points of light and start seeing the shapes behind them. This is that moment. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Ahead, we will trace the tools that establish distance, enter Andromeda's layered interior, and chart its surrounding company. We will meet grand spirals, altered remnants, and elusive dwarves, then follow the hidden forces connecting every scale, and by the end, even our neighborhood may no longer seem like a neighborhood at all. You look up on a clear autumn night, far from the glow of cities, and if you know where to aim your eyes, you can see it, a faint smudge of light in the constellation Andromeda. Most people who notice it at all assume it's a star that's slightly out of focus or a trick of tired vision. It isn't. What you're looking at is a galaxy, not a distant speck at the edge of the observable universe, but the nearest large galaxy to our own, a structure containing roughly 1 trillion stars, sitting just 2.5 million light-years away. And here's the part that breaks most people's sense of scale when they first hear it. That faint smudge, if your eyes were sensitive enough to see its full extent, would appear 6 times wider than the full moon, 6 times. The object you're casually glancing past on your way to find Orion or the Pleiades is actually dominating a massive section of the sky. You just can't see most of it because your eyes aren't built to detect the faint outer regions of a galaxy millions of light-years away. But it's there, all of it, looming. Andromeda, catalogue designation Messier 31, has been lying to us by omission. Not because it's hiding, but because the way we talk about it, the way we picture it, the way we file it away in our mental map of the cosmos, undersells what it actually is. We call it our neighbor. We say it's nearby. We treat it like the house next door. That framing is wrong. Andromeda isn't next door. It's a continent-sized shadow hanging over the yard, moving closer every second. And the Milky Way, our home, the galaxy we've spent centuries mapping and studying and romanticizing, is smaller. We are the smaller galaxy. Andromeda is the largest galaxy in the local group, the cluster of roughly 80 galaxies bound together by gravity in this corner of the universe. It outweighs us, it outnumbers us in stars, and it is coming. Let's start with the size, because that's where the first crack in perception opens. When astronomers measure Andromeda's diameter, they get different numbers depending on what they're measuring. The bright visible disk, the part that shows up cleanly in most telescope images, spans about 220,000 light-years from edge to edge. For comparison, the Milky Way's visible disk is somewhere between 100,000 and 120,000 light-years across, depending on whose measurement you trust. Andromeda is roughly twice as wide, but that's just the part that glows brightly enough to photograph easily. The actual structure, the full extent of Andromeda's gravitational influence, its halo of old stars, its diffuse outer gas, stretches much farther. Some estimates push the total diameter past 260,000 light-years when you include the faint halo material that surrounds the bright core like a fog. Here's a way to picture that span. Light, the fastest thing in the universe, the thing that crosses the 93 million miles from the Sun to Earth in 8 minutes, would take 220,000 years to travel from one side of Andromeda's visible disk to the other. If a photon left the eastern edge of Andromeda around the time early Homo sapiens were figuring out how to make fire, it would only just now be arriving at the western edge. That is the width of a single galaxy, one object. And we see the whole thing, compressed by distance, into a smudge barely noticeable without a telescope. Inside that structure are approximately 1 trillion stars, not a rough estimate that could be off by a factor of 2, a trillion. The Milky Way, our own galaxy, contains somewhere between 200 and 400 billion stars, depending on how you count the faint red dwarfs that make up the bulk of the population. Andromeda has more than double that, possibly triple. Every single one of those stars is a sun, many with their own planets, their own asteroid belts, their own cosmic neighborhoods, playing out the same physics we see in our own solar system. 1 trillion separate furnaces, each burning hydrogen into helium, scattered across 220,000 light-years of space, all held together by gravity into a single rotating structure. The scale stops being a number you can picture and starts being a thing you just accept because the alternative is staring at the wall, trying to count to 1 trillion. Andromeda's mass is harder to pin down precisely, but current estimates put it at roughly 1.5 trillion times the mass of our Sun, when you include the dark matter halo. Dark matter, the invisible scaffolding that makes up most of the mass in every galaxy, doesn't glow. It doesn't emit light. It doesn't interact with anything except gravity. We only know it's there because without it, galaxies like Andromeda would fly apart. The stars are moving too fast. The outer regions are rotating at speeds that, according to the visible mass alone, should fling them into intergalactic space like sparks off a grinding wheel. They don't. Something else is holding them in. That something is dark matter, and Andromeda is swimming in it. Now comes the part that changes the story from interesting to unavoidable. Andromeda is moving toward us, not drifting, not slowly closing the gap over some unimaginable stretch of deep time, moving at 110 kilometers per second. Every second, Andromeda gets 110 kilometers closer to the Milky Way. Right now, as you read this, the distance between the two galaxies is shrinking. In the time it took you to read the last paragraph, Andromeda closed the gap by several thousand kilometers. By tomorrow, it will be millions of kilometers closer. By next year, billions. The collision is not a possibility. It is not something that might happen if conditions line up a certain way. It is scheduled. The math has been done. The trajectories have been mapped. In roughly 4.5 billion years, give or take a few 100 million, depending on the model, Andromeda and the Milky Way are going to collide. When astronomers say collide, they don't mean the two galaxies will smash into each other like cars in a head-on crash. Galaxies are mostly empty space. The stars inside them are so far apart that when two galaxies merge, the stars themselves almost never actually hit each other. What happens instead is stranger and slower. The two galaxies will pass through each other, their gravity pulling and stretching and warping the structure of both. Stars will be flung out into new orbits. Gas clouds will compress and ignite, triggering massive waves of star formation. The supermassive black holes at the center of each galaxy, Sagittarius A star in the Milky Way, and the slightly larger black hole at Andromeda's core, will spiral inward over millions of years and eventually merge into a single, even larger monster. The process will take billions of years to complete, and when it's over, the two galaxies will no longer exist as separate objects. They will have become one. The astronomers working on the models have already named the result. They call it Milkdromeda. Not an official scientific designation, just the nickname that stuck, because it's the only name that makes sense. Milky Way plus Andromeda equals Milkdromeda. By the time the merger completes, assuming Earth is still around and hasn't been swallowed by the sun during its red giant phase, the night sky will look nothing like it does now. The familiar constellations will have drifted and distorted beyond recognition. The Milky Way's band of light, that river of stars we see stretching across the summer sky, will be gone. In its place will be the scattered glow of a massive elliptical galaxy, a football-shaped swarm of stars with no clear disk, no spiral arms, just a dense glowing core surrounded by a halo of stellar chaos. None of this affects you personally. The sun will likely be ejected into a completely different region of the merged galaxy, possibly flung into the outer halo where stars are sparse and the space between them is measured in light years instead of the few light years that separate us from our current neighbors. But the sun will still shine, the planets will still orbit. If Earth survives the sun's expansion into a red giant, which is a separate and much nearer-term problem, then it will still be here, still orbiting, still spinning through space, in a galaxy that no longer resembles the one we grew up in. The skies will change, the stars will move. The Andromeda smudge that you can barely see tonight will have consumed us entirely. It's worth pausing on what that collision means for our sense of place in the universe. For most of human history, we thought Earth was the center of everything. Then we learned we orbit the sun. Then we learned the sun is one star among hundreds of billions in a galaxy. Then we learned that galaxy is one among hundreds of billions in the observable universe. Each step pushed us farther from the center, farther from significance, until we became a speck on a speck orbiting a speck in a universe so large that our entire galaxy is a rounding error. And now we learn that even our galaxy, the structure we thought of as permanent, is temporary. It has an expiration date, not because it's dying, but because it's merging with something larger. We are being absorbed. Our cosmic address is about to change, and there's nothing we can do but watch. That might sound bleak. It isn't. The collision is one of the most spectacular events the universe can produce, and we are sitting in front row seats with 4.5 billion years to wait for the show. By the time Andromeda and the Milky Way finally begin their merger in earnest, humans, if we still exist in any form recognizable to the species walking around today, will have had time to spread across the galaxy, possibly beyond it. We will have had time to witness the slow approach, to measure the changing distance year by year, to watch as Andromeda grows in the sky from a faint smudge to a glowing disk to a structure so large it dominates the entire night hemisphere. Assuming our descendants are still looking up, still curious, still asking what comes next, they will see one of the rarest and most beautiful processes in the cosmos unfolding in real time. The birth of a new galaxy from the wreckage of two old ones. But even now, even from 2.5 million light-years away, Andromeda is not a distant abstraction. It is close enough that if you know when to look and you have dark skies, you can see it with your naked eyes, not as a detailed spiral, not with arms and dust lanes and star clusters, just as a faint patch of light, a smudge. The photons hitting your eyes tonight left Andromeda 2.5 million years ago, when the Milky Way's spiral arms were in slightly different positions and Earth was occupied by species that no longer exist. Those photons have been traveling through the void ever since, crossing the empty space between galaxies, threading through the scattered gas clouds of the intergalactic medium, until they finally arrived here, tonight, and landed on your retina. That smudge is the light of 1 trillion suns, compressed by distance into something your brain barely registers as worth noticing. And it's getting closer. Every second, Andromeda moves 110 kilometers nearer. In 1 year, it closes the gap by about 3.5 billion kilometers. That sounds like a lot, until you remember that the distance separating us right now is roughly 24 quintillion kilometers. Andromeda has a long way to go, but it is going. The collision is inevitable, not because someone decided it, but because gravity doesn't negotiate. The two galaxies are locked in each other's pull, and there is no force in the universe strong enough to stop what's coming. The story of Andromeda is not just the story of a neighboring galaxy. It's the story of scale and time and the slow, patient mechanics of a universe that operates on timelines so long they make human history look like a blink. It's the story of structures so large that light takes hundreds of thousands of years to cross them, and yet those structures are moving, colliding, merging, dying, and being born again in cycles that have been running since the first galaxies formed more than 13 billion years ago. Andromeda is not a neighbor. It is the next chapter in the Milky Way's story, and that story is already written in the trajectories and the math. All we can do is wait and watch. And once you understand what Andromeda actually is, once you see past the faint smudge and grasp the trillion-star behemoth hiding behind it, the question becomes unavoidable. If Andromeda is that massive, that close, and that much larger than the Milky Way, what else is out there? What other galaxies are drifting through the local group, the cluster of roughly 80 galaxies bound together in this corner of the universe? What shapes do they take? What sizes, what stories are they telling? Because Andromeda, for all its scale and drama, is just one type of galaxy. The local group contains others: spirals, ellipticals, irregulars, dwarves, each one a different shape, a different history, a different way of organizing matter and energy into something stable enough to last billions of years. Andromeda is the giant, but it is not alone. Andromeda is a spiral galaxy, and so is the Milky Way. That sentence carries more weight than it might seem at first. When astronomers sorted galaxies into categories in the early 20th century, they weren't just organizing shapes for convenience. They were identifying fundamentally different kinds of objects, structures that formed under different conditions and behave in different ways over cosmic time. Spiral galaxies are one of those categories, and they represent some of the most dynamic, active, and visually striking objects in the universe. They are not the most common type, they are not the oldest, but they are the ones doing the most right now, and understanding what makes them spiral, what keeps them spinning, and what happens inside those elegant swirling arms is essential to understanding what the local group actually is. A spiral galaxy has 4 main components, and every one of them matters. At the center sits the bulge, a dense, spherical or football-shaped concentration of old stars packed tightly around the galaxy's core. In most spirals, including Andromeda and the Milky Way, the bulge also contains a supermassive black hole, not a small black hole left over from a dead star, but a gravitational monster weighing millions or billions of times the mass of the Sun. Andromeda's central black hole is estimated at roughly 100 to 230 million solar masses, depending on the model. The Milky Way's black hole, Sagittarius A star, weighs about 4 million solar masses. Andromeda's is bigger, not by a little, by a factor of 25 or more. That difference tells you something about how the two galaxies grew up. Andromeda has been eating. It has been pulling in smaller galaxies, merging with them, feeding its core, building mass over billions of years. The Milky Way has done some of that too, but Andromeda did it more aggressively. Surrounding the bulge is the disk, a flattened structure of stars, gas and dust, spread out across hundreds of thousands of light years. The disk is where most of the visible action happens. It's where new stars are born, where spiral arms trace bright lanes of fresh blue stars and glowing hydrogen clouds, where the galaxy looks alive. The disk rotates, not as a solid object, the way a vinyl record spins, but differentially. Stars closer to the center orbit faster than stars farther out, though not by as much as you'd expect if all the mass were concentrated in the core. That mismatch between observed rotation speed and predicted rotation speed is one of the strongest pieces of evidence for dark matter. Something invisible is holding the outer parts of the disk together, keeping them rotating faster than they should, and that something outweighs all the visible stars and gas combined. The spiral arms themselves are not permanent structures. This is one of the more counterintuitive facts about spiral galaxies, and it took astronomers decades to figure out. When you look at an image of Andromeda or the Milky Way, the spiral arms look solid, like trails of stars carved into the disk. They aren't. The arms are density waves, regions where stars and gas bunch up temporarily as they orbit. Imagine cars on a highway slowing down as they pass through a construction zone. The zone doesn't move with the cars, it stays in place while cars flow through it. Spiral arms work the same way. Stars drift into the arm, slow down slightly, then drift out the other side. While they're in the arm, the increased density triggers star formation. Gas clouds that were drifting peacefully through empty space suddenly find themselves compressed by the gravity of all the other gas clouds and stars piling up in the same region. Compression heats the gas. Heat and pressure trigger collapse. Collapse ignites fusion. Stars are born. That's why spiral arms glow blue. Blue stars are young stars, massive and hot, burning through their fuel at a ferocious rate. They only live a few million years before going supernova, which in galactic terms is barely a blink. By the time a blue star drifts out of the spiral arm and into the quieter regions between the arms, it's often already dead. The arm itself keeps glowing because new blue stars are constantly being born inside it. The structure persists even though the individual stars lighting it up are changing all the time. It's a wave, not a jog, a pattern in motion. Andromeda has at least 2 major spiral arms, though the exact count depends on how you define a major arm versus a minor spur. The galaxy's disk is tilted relative to our line of sight, so we see it at an angle rather than face on. That tilt has made it harder to map the arms precisely, but long exposure images from Hubble and other telescopes have traced them clearly enough to show that the structure is not perfectly symmetric. One arm is slightly more prominent than the other. There are spurs and branches breaking off in places. The disk has been disturbed, probably by past interactions with smaller galaxies that got too close and were torn apart by tidal forces. Andromeda's history is written into the shape of its arms, and the story they tell is one of violence smoothed over by time. The Milky Way has a similar structure, though mapping it from the inside is vastly more difficult. When you're sitting inside a galaxy, you can't step back and take a wide-angle photo. You have to infer the shape from what you can see in every direction, piecing together distance measurements, star counts, and observations of gas clouds to build a model of the whole. The current best estimate is that the Milky Way has 4 major spiral arms, though some models argue for 2 primary arms with several smaller offshoots. The details are still being argued over. What's not in dispute is that we live in a spiral galaxy with active star formation, a rotating disk, and a structure broadly similar to Andromeda's. We are not identical twins, but we are clearly siblings. Same family, same basic architecture, same physics running the show. The 4th component of a spiral galaxy is the halo, and this is where things get strange. The halo is a roughly spherical cloud of old stars, globular clusters, and dark matter that surrounds the visible disk and extends far beyond it. In Andromeda, the stellar halo has been traced out to more than 200,000 light-years from the core, and the dark matter halo goes even farther. Some estimates push the total gravitational influence of Andromeda's dark matter halo out past 1 million light-years, which means the galaxy's true size dwarfs the bright disk you see in photographs. The halo doesn't glow brightly. The stars inside it are old, red, and dim. They're the survivors from the galaxy's early days, the stars that formed in the chaotic first billion years after the Big Bang, when galaxies were still assembling from smaller clumps of matter. Many of the stars in Andromeda's halo didn't form there at all. They formed in smaller galaxies that Andromeda cannibalized over billions of years. When a dwarf galaxy gets too close to a spiral giant, tidal forces rip it apart. The stars don't vanish. They get scattered into the halo, joining the diffuse cloud of old stars that marks the graveyard of every galaxy Andromeda has ever consumed. The Milky Way has a halo too, and we can study it in more detail because we're sitting inside it. Astronomers have identified streams of stars in our halo that clearly came from disrupted dwarf galaxies. The Sagittarius dwarf elliptical galaxy is being torn apart right now, stretched into a long, thin stream that wraps around the Milky Way like a ribbon. The stars in that stream are still orbiting the galaxy, but they no longer belong to a coherent structure. Their home galaxy is dead. They're orphans now, drifting through the halo until they eventually settle into some new equilibrium or get flung out into intergalactic space entirely. This process of galactic cannibalism is not rare. It's standard. Every large spiral galaxy has a halo full of the remnants of smaller galaxies it devoured. Andromeda's halo contains the ghosts of dozens of past meals, and the Milky Way's halo will eventually contain Andromeda's stars once the merger completes billions of years from now. Star formation in spiral galaxies happens almost entirely in the disk. The bulge is too hot and dense. Stars there formed billions of years ago and have long since settled into stable orbits. The halo is too diffuse. There's not enough gas to collapse into new stars. The disk is the sweet spot. It has enough gas, enough dust, and enough gravitational structure to keep the star formation process running. Spiral arms compress the gas. Compression triggers collapse. Collapse ignites stars. Those stars heat the surrounding gas with radiation and stellar winds, which can either shut down further star formation by blowing the gas away, or trigger more collapse by compressing nearby clouds. It's a chaotic feedback loop, and the result is that star formation in spiral galaxies happens in bursts, concentrated in specific regions rather than smoothly across the whole disk. Andromeda's disk contains enormous clouds of hydrogen gas, the raw material for stars. Hydrogen doesn't glow on its own unless something heats it up, So astronomers map it using radio telescopes that can detect the faint emission line hydrogen produces at a wavelength of 21 centimeters. Those maps show that Andromeda has vast reserves of gas still available for star formation. It's not running out anytime soon. The star formation rate in Andromeda is lower than it was a few billion years ago, which is typical for large spirals. They tend to form stars aggressively in their youth and then slow down as they age and their gas supplies get used up or blown out by supernovae. But Andromeda is still active, it's still making stars, it's still alive in the way that matters for galaxies. The Milky Way's star formation rate is estimated at roughly 1 to 2 solar masses per year. That means every year, the combined mass of all the new stars being born in our galaxy adds up to about 1 or 2 times the mass of the Sun. That might sound slow, and it is compared to the violent starburst galaxies that can crank out hundreds of solar masses worth of stars per year during a merger or collision. But it's enough to keep the galaxy looking young. Andromeda's star formation rate is similar, maybe slightly higher, depending on which study you trust. Both galaxies are in what astronomers call a quiescent phase. They're not dead, but they're not in a frenzy either. They're middle-aged, still working, but past their prime. One of the more surprising discoveries about Andromeda came from mapping its rotation. If you measure how fast stars are moving at different distances from the galaxy's core, you can build a rotation curve. In a simple universe where all the mass is in the stars and gas you can see, the rotation curve should drop off steeply as you move outward. Stars far from the core should be orbiting slowly because there's not much mass pulling on them. That's how planets behave in the solar system. Neptune orbits much more slowly than Earth because it's farther from the Sun. Andromeda's rotation curve doesn't drop, it stays flat. Stars at the outer edge of the disk are moving just as fast as stars closer in, which means there's a huge amount of invisible mass holding them in place. That invisible mass is dark matter, and it outweighs everything else in the galaxy by a factor of at least 5 to 1. You can't see it, you can't touch it. You can only infer its existence from the way it pulls on the things you can see. Every spiral galaxy studied so far shows the same flat rotation curve, which means dark matter isn't just a quirk of Andromeda. It's a fundamental ingredient in how galaxies work. Andromeda is not alone. It has a retinue of smaller galaxies orbiting it, bound by gravity into a system that mirrors the way planets orbit a star. These satellite galaxies are not spirals. Most of them are dwarf spheroidals or dwarf ellipticals, small faint structures with just a few million to a few billion stars. They orbit Andromeda over hundreds of millions of years, drifting through the halo, occasionally getting close enough to the main galaxy to feel tidal forces that stretch and distort them. Some will survive, others won't. The ones that get too close will be torn apart and their stars will be added to Andromeda's halo, just like the galaxies that came before them. The Milky Way has the same setup. We have dozens of satellite galaxies, including the large and small Magellanic Clouds, which are visible from the southern hemisphere as two bright smudges in the night sky. Those galaxies are slowly falling into the Milky Way. It will take billions of years, but the outcome is inevitable. They will be consumed. The gravitational dance between a large spiral and its satellites is one of the key processes shaping how galaxies evolve. Every time a dwarf galaxy passes near a spiral, the encounter transfers energy and angular momentum. The dwarf gets stretched, the spiral's disk gets disturbed. Gas clouds in the dwarf can be compressed, triggering a burst of star formation before the galaxy is torn apart entirely. The spiral gains mass, the dwarf loses it. Over billions of years, the spiral grows by cannibalizing everything around it, and the population of dwarf galaxies in the local group slowly shrinks. Andromeda has done this more than the Milky Way, which is part of why it's larger. It sits at the center of its own subgroup within the local group, with more satellites orbiting it than the Milky Way has. It's the dominant structure in this corner of the universe, and it got that way by eating its neighbors. There's a certain elegance to the way spiral galaxies work. They're not static, they're not frozen, they rotate, they form stars, they interact with their satellites, they evolve. The spiral arms are waves, the stars drift through them, the gas compresses, collapses, ignites. New stars light up the arms and then drift out into the disk, slowly cooling and reddening as they age. The whole system is in motion, every piece pulling on every other piece, held together by gravity and dark matter into a structure stable enough to last billions of years. And yet, nothing about a spiral galaxy is permanent. The arms shift, the disk thickens, the halo grows. Stars are born and stars die. The galaxy changes, but the changes are so slow that from any human perspective, the structure looks eternal. Andromeda and the Milky Way are the two largest spirals in the local group, and together they dominate the gravitational landscape. Their combined mass outweighs everything else in the cluster by a wide margin. The other galaxies in the group, the smaller spirals, the ellipticals, the irregulars, the dwarfs, all of them are bit players in a drama centered on these two giants. And in 4.5 billion years, the drama reaches its climax. The two spirals will collide, merge, and form something new. The spiral arms will be destroyed. The disks will be scrambled. The bulges will merge. The supermassive black holes at the cores will spiral inward and combine. What emerges will be a single massive elliptical galaxy, a structure with no disk, no arms, no ongoing star formation. Just a swarm of old stars orbiting a central core in random directions. The age of spirals in the local group will be over, but that's still billions of years away. For now, Andromeda and the Milky Way are the pillars of the local group, the largest and most active galaxies in the cluster. They define what a spiral galaxy is, how it works, and what it can become. They are the template, the archetype, the standard by which every other spiral in the universe is measured. And while they are the largest spirals in the group, they are not the only ones. There are smaller spirals out there, quieter siblings that don't get as much attention but are just as important to the story. Galaxies like Triangulum, which orbits on the edge of the group, or the smaller spirals buried in the noise of dwarf galaxies and irregular structures. Those galaxies are next, and understanding them means understanding the full range of what a spiral can be, from giants like Andromeda down to the smallest structures still clinging to the spiral shape. Andromeda and the Milky Way are the giants, the headline acts, the two spirals everyone talks about when the local group comes up in conversation. But they are not the only spirals in the neighborhood. Sitting roughly 3 million light-years away, tilted at an angle that shows off its spiral arms like a blueprint laid flat on a table, is Triangulum, Messier 33, the third largest galaxy in the local group, and the one that keeps reminding astronomers that size is not the only thing that matters. Triangulum is smaller than Andromeda and the Milky Way by a significant margin. It is also louder, not in the sense that it emits sound, obviously, but in the sense that, for a galaxy of its size, it is doing a lot. More star formation than it has any right to. More activity in its spiral arms than you would expect. More noise in the data than a quiet middle sibling should be making. Triangulum is punching above its weight, and the more closely astronomers look at it, the stranger it gets. Let's start with the basics, because Triangulum does not get nearly as much attention as it deserves. The galaxy sits about 2.9 to 3 million light-years from Earth, depending on whose distance measurement you trust. That makes it slightly farther away than Andromeda, but still absurdly close in cosmic terms. Close enough that under perfect conditions, far from city lights, with no moon in the sky and your eyes fully adapted to the dark, you can see it with your naked eyes, not as a detailed spiral, not with arms and star clusters, just as a faint smudge, a ghostly patch of light in the constellation Triangulum. Most people who claim to have seen it are either lying or mistaken. It is genuinely difficult to spot without optical aid. But it is there, and it is visible, which makes Triangulum one of the most distant objects a human being can see without a telescope. The photons hitting your retina left that galaxy 3 million years ago, when early human ancestors were just beginning to figure out how to use tools. Those photons have been traveling through the void ever since, and they are arriving right now, faint and patient, carrying the light of a galaxy most people have never heard of. Triangulum is a spiral galaxy, but it is not a giant. Its diameter is somewhere between 50,000 and 61,000 light-years, depending on how you measure the outer edges of the disk. For comparison, the Milky Way spans roughly 100,000 to 120,000 light-years, and Andromeda stretches past 220,000 light-years when you include its full visible disk. Triangulum is half the size of the Milky Way and less than a third the size of Andromeda. It is smaller in mass too. The Milky Way contains somewhere between 200 and 400 billion stars. Andromeda has 1 trillion. Triangulum has about 40 billion. That is still an incomprehensible number. 40 billion separate suns, each one a furnace burning hydrogen into helium, scattered across tens of thousands of light-years. But in the context of the local group, 40 billion stars makes Triangulum the little sibling, the one that gets overlooked because the bigger galaxies are standing in the way. Mass estimates for Triangulum vary depending on the study, but most land somewhere between 10 and 50 billion solar masses when you include the dark matter halo. That is a huge range, and the uncertainty reflects how difficult it is to weigh a galaxy when you cannot see most of what is in it. The stars and gas you can detect with telescopes only account for a fraction of the total mass. The rest is dark matter, and dark matter does not glow. You have to infer its presence from the way the galaxy rotates, from the speeds of stars in the outer disk, from the gravitational pull holding the whole structure together. Triangulum rotates like a spiral should, with a flat rotation curve that tells you there is far more mass present than the visible matter alone can explain. The dark matter halo extends well beyond the visible disk, wrapping the galaxy in an invisible shell that outweighs everything you can see by at least a factor of 5. Despite being smaller than the Milky Way and Andromeda, Triangulum is not quieter. In fact, it is noisier. The star formation rate in Triangulum is unusually high for a galaxy of its size. Some studies estimate it at several times higher than Andromeda's rate, possibly even higher than the Milky Way's, depending on the measurement. That means Triangulum is churning out new stars at a pace that does not match its mass. Smaller galaxies are supposed to run out of gas faster. They are supposed to slow down, age, cool off. Triangulum is doing the opposite. It is still forming stars aggressively, still lighting up its spiral arms with young blue stars and glowing hydrogen clouds, still behaving like a galaxy in its youth, even though it is billions of years old. Nobody is entirely sure why. The leading theory is that Triangulum has managed to hold on to more of its gas than other galaxies its size, possibly because it has not been involved in as many violent interactions or mergers that would strip away its star-forming material. Or possibly because it is stealing gas from somewhere else. Galaxies do that. They pull in material from their surroundings, from intergalactic gas clouds, from smaller galaxies that wander too close. Triangulum might be quietly siphoning fuel from the space around it, keeping its star formation engines running long past the point where a galaxy its size should have gone quiet. The spiral arms in Triangulum are some of the most prominent and well-defined in the local group. The galaxy is tilted at an angle that gives us a nearly face-on view, which means we can see the arms clearly without having to peer through the edge of the disk. That angle has made Triangulum a favorite target for astronomers studying spiral structure, star formation, and the physics of density waves. The arms glow brightly in ultraviolet and infrared, lit up by young massive stars and the warm dust heated by their radiation. Embedded in those arms are enormous regions of ionized hydrogen, glowing clouds of gas called H2 regions where star formation is happening right now. Some of those regions are among the largest and brightest known in the local group. One in particular, catalogued as NGC 604, is a monster. It spans roughly 1,500 light-years across, making it one of the largest star-forming regions ever observed. For comparison, the Orion Nebula, the most famous star-forming region visible from Earth, is only about 24 light-years across. NGC 604 is more than 60 times larger. Inside it are more than 200 hot, massive stars, all born within the last few million years, all pumping out radiation that ionizes the surrounding gas and makes the whole region glow like a beacon. If NGC 604 were sitting where the Orion Nebula is, roughly 1,300 light-years from Earth, it would cover a significant portion of the night sky and be visible in daylight. Triangulum's high star formation rate and its prominent H2 regions make it a useful laboratory for studying how galaxies build stars. Spiral arms are density waves, regions where gas piles up temporarily as it orbits through the disk. When the gas gets compressed, it collapses under its own gravity and ignites into stars. The stars that form inside the density wave are massive and short-lived. They burn hot and blue, blasting the surrounding gas with radiation and stellar winds. Within a few million years, the most massive stars go supernova, exploding and scattering heavy elements into the surrounding clouds. Those heavy elements, carbon, oxygen, nitrogen, iron, all the stuff that was not present in the universe right after the Big Bang, get mixed into the next generation of gas clouds. The next generation of stars that forms will contain those elements. And over billions of years, the galaxy enriches itself, building up heavier and heavier elements with each cycle of star formation and death. Triangulum is in the middle of that process right now, cranking out stars, enriching its gas, building the raw materials for planets and eventually life, assuming any of those planets end up in the habitable zone around a stable star. One of the surprises about Triangulum is that it might not have a supermassive black hole at its center. Most large galaxies do. Andromeda has one weighing 100 to 230 million solar masses. The Milky Way has Sagittarius A star at about 4 million solar masses. Even smaller galaxies tend to have central black holes, though the relationship between galaxy mass and black hole mass is not perfectly understood. Triangulum appears to be an exception. Observations of the galaxy's core have not found the kind of rapidly moving stars or intense radiation signature you would expect if a supermassive black hole were sitting there. Either the black hole is much smaller than expected, or it is not there at all. If Triangulum truly lacks a supermassive black hole, it would be one of the largest galaxies known to break the pattern, and astronomers would have to revisit their models of how galaxies and black holes co-evolve. It is possible the black hole is just hiding, too small or too quiet to detect from this distance. Or it is possible Triangulum formed differently, assembled its mass in a way that did not funnel enough material into the core to seed a massive black hole in the first place. The question is still open. Triangulum also contains at least one unusually massive stellar black hole, a remnant of a dead star rather than a supermassive monster. The system is called M33X7, and it consists of a black hole weighing roughly 16 solar masses orbiting a companion star. The black hole is pulling gas off the companion, heating it to millions of degrees as it spirals inward, and the system emits X-rays bright enough to be detected from 3 million light-years away. M33X7 is one of the most massive stellar black holes ever confirmed, and its existence tells you that Triangulum has been forming and destroying massive stars for billions of years. Every supernova leaves behind either a neutron star or a black hole, depending on how heavy the original star was. Over time, those remnants accumulate. Some of them end up in binary systems where they can feed on a companion star. Some drift alone through the galaxy, invisible and silent. M33X7 is one of the loud ones, and its presence is a reminder that even in a galaxy as visually beautiful and active as Triangulum, death is constantly happening in the background. The relationship between Triangulum and Andromeda is one of the more interesting open questions in local group dynamics. Some astronomers think Triangulum is gravitationally bound to Andromeda, orbiting the larger galaxy the way a moon orbits a planet. If that is true, Triangulum would be a satellite galaxy, the largest satellite in Andromeda's retinue by a wide margin. Other astronomers are not convinced. Triangulum is moving at roughly 100,000 kilometers per hour relative to the Milky Way system, and its trajectory suggests it might be on a long elliptical orbit around Andromeda, or it might be passing through the local group on a path that will take it somewhere else entirely. The data are ambiguous. Measuring the proper motion of a galaxy 3 million light-years away is difficult. You can measure how fast it is moving toward or away from you using the Doppler shift of its light, but measuring its motion across the sky, the sideways component, requires extremely precise measurements of how its position changes over time. Those measurements are possible now thanks to missions like Gaia, which has mapped the positions and motions of billions of stars in the Milky Way and nearby galaxies. But the uncertainties are still large enough that the question of whether Triangulum is bound to Andromeda or just passing by remains unsettled. If Triangulum is bound to Andromeda, the implications are significant. It would mean the Andromeda system is even more massive than direct measurements suggest, because Triangulum's orbit would be tracing out the shape of Andromeda's dark matter halo. It would also mean Triangulum's future is sealed. Satellite galaxies do not last forever. Over billions of years, tidal forces from the larger galaxies stretch and distort them. Gas gets stripped away. Stars get pulled out into long streams. Eventually, the satellite is torn apart completely, and its stars are absorbed into the halo of the larger galaxy. If Triangulum is orbiting Andromeda, it will eventually be consumed, just like every other satellite Andromeda has ever captured. The process will take billions of years, long enough that Triangulum will still be recognizable as a spiral for most of that time. But the end is inevitable. Andromeda eats everything that gets too close. Even if Triangulum is not bound to Andromeda, it is still part of the local group, and that means it is involved in the gravitational dance between all the galaxies in the cluster. The local group is not a static collection of objects sitting quietly in space. It is a dynamically evolving system where every galaxy pulls on every other galaxy. Andromeda and the Milky Way are the two largest masses, so they dominate the gravitational landscape. Everything else, Triangulum included, is responding to their pull. Over the next few billion years, as Andromeda and the Milky Way move closer together, the gravitational field of the combined system will get stronger. Smaller galaxies will feel that pull more acutely. Some will be flung out into intergalactic space, ejected from the group entirely. Others will fall inward and be absorbed. Triangulum's fate depends on the details of its current trajectory, and those details are not yet fully nailed down. It might survive the merger between Andromeda and the Milky Way, drifting on the outskirts of the resulting elliptical galaxy, slowly losing stars to tidal stripping, but maintaining some kind of coherent structure for a while longer. Or it might fall into the chaos, collide with one of the merging giants, and be torn apart in the process. Either way, the triangulum we see today, with its bright spiral arms and active star formation, is temporary. Galaxies do not last forever in the form they currently hold. Triangulum has at least one confirmed satellite galaxy of its own, a dwarf galaxy called the Pisces Dwarf. The Pisces Dwarf is tiny, faint, and utterly unremarkable, except for the fact that it exists. Its presence tells you that even a mid-sized spiral like Triangulum has enough gravitational pull to hold on to smaller companions. The hierarchy repeats at every scale. Andromeda has satellites, the Milky Way has satellites, Triangulum has satellites. Those satellites might have satellites of their own, though at that scale the structures become so faint and diffuse that detecting them is nearly impossible. The local group is not a democracy, it is a hierarchy with mass determining influence. The largest galaxies dominate. The smaller galaxies orbit, merge, or get torn apart. And the smallest galaxies, the dwarfs, the irregulars, the faint smudges barely distinguishable from noise, drift through the spaces in between, occasionally getting pulled into a larger structure and disappearing entirely. Beyond Triangulum, the population of spirals in the local group drops off sharply. There are a few smaller spiral or irregular spiral galaxies scattered around the group, but none of them come close to the size or prominence of Andromeda, the Milky Way, or Triangulum. Some of them are difficult to classify cleanly. A galaxy with hints of spiral structure, but too much chaos to call it a proper spiral, might get labeled as an irregular or a transitional type. The boundaries between categories are not always sharp. Galaxies are messy. They interact, merge, get distorted by tidal forces, lose their gas, have their star formation shut down by radiation from nearby galaxies, or by collisions that heat their gas beyond the point where it can collapse. The result is a population of objects that do not fit neatly into the textbook categories, spirals that are not quite spirals anymore, ellipticals that still have hints of disk structure buried in their cores, irregulars that might have been spirals once but got wrecked by a close encounter and never recovered. The smaller spirals and irregular galaxies in the local group are important not because they dominate the mass or the light, but because they represent the diversity of outcomes possible when you give gravity, gas, and dark matter billions of years to play out different scenarios. Some galaxies form in dense environments where interactions are frequent and they get battered into ellipticals or irregulars. Some form in isolation, far from the gravitational influence of larger neighbors, and they grow slowly and quietly into well-defined spirals. Triangulum sits somewhere in the middle. It is close enough to Andromeda and the Milky Way to feel their influence, but not so close that it has been destroyed. It has managed to hold on to its spiral structure, its gas, its star formation, longer than smaller galaxies in similar positions. That tells you something about how resilient spiral structure can be, and how much abuse a galaxy can take before it loses the features that define it. The concept of galactic hierarchy is central to understanding how the local group works. Mass determines influence. The most massive galaxies pull on everything around them. They capture satellites, strip gas from smaller neighbors, grow larger by cannibalizing everything that gets too close. The less massive galaxies respond to that pull. They orbit, they merge, they get torn apart. The hierarchy is not stable. It evolves over billions of years as galaxies collide, merge, and redistribute their mass. 4.5 billion years from now, when Andromeda and the Milky Way complete their merger, the hierarchy will shift. The two largest galaxies will become one even larger galaxy, and everything else in the group will have to adjust to the new gravitational landscape. Triangulum will either survive as a satellite of the merged system, or it will fall in and be absorbed. The smaller galaxies, the dwarfs and irregulars, will drift or fall or get ejected depending on their positions and velocities at the time of the collision. The local group as it exists today, with its clear division between two large spirals and a crowd of smaller companions, is temporary. In a few billion years, the structure will look completely different. But for now, Triangulum is still here, still forming stars, still glowing brightly in its spiral arms, still holding on to its gas and its structure, despite being surrounded by larger neighbors that could tear it apart if it drifted too close. It is the third largest spiral in the local group, and while it will never get the attention that Andromeda and the Milky Way command, it is just as important to the story. Triangulum is proof that you do not need to be the largest galaxy in the room to be interesting. You just need to be loud enough that people notice when they finally get around to looking. And once you have accounted for the spirals, the galaxies with disks and arms and active star formation, the next question becomes unavoidable. What about the galaxies that stopped forming stars billions of years ago? The ones that burned through their gas supplies, shut down their spiral arms, and settled into a stable configuration of old stars drifting in random orbits. The ones that look nothing like Andromeda or Triangulum, that glow a dull red instead of a vibrant blue, that have no disk, no structure, no sign of the chaos that keeps spiral galaxies looking alive. Those galaxies exist, and they are closer than you might think. They are ellipticals, the stellar graveyards of the local group, and understanding what they are and how they got that way is the next piece of the puzzle. Triangulum is still forming stars, still glowing, still holding on to its spiral structure, despite being surrounded by neighbors that could tear it apart if it wandered too close. But not every galaxy in the local group looks like that. Not every galaxy is still alive in the sense that matters. Some galaxies stopped forming stars billions of years ago. They burned through their gas, shut down their spiral arms, and settled into a kind of cosmic retirement where nothing new happens and nothing ever will. They are smooth, they are red, they are old, and they represent one of the most common endpoints a galaxy can reach. These are the ellipticals, and understanding what they are means understanding what happens when a galaxy runs out of fuel, loses its structure, or collides with something else hard enough to scramble everything it once was. The local group has several of them, and while they do not dominate the population the way ellipticals do in larger galaxy clusters, their presence tells a story about violence, time, and the slow grinding process that turns a dynamic spiral into a featureless ball of ancient stars. Elliptical galaxies do not have spiral arms. They do not have disks. They do not have the bright blue glow of young massive stars lighting up their outer regions. What they have instead is a smooth, nearly featureless distribution of old stars arranged in a roughly spheroidal or football-shaped blob. If you take a photograph of an elliptical galaxy, it looks like someone smeared light across the image in a gentle gradient, brightest at the center and fading smoothly toward the edges. No structure, no lanes of dust, no regions of active star formation. Just stars, billions of them, drifting in random orbits around a common center of mass. The stars are not organized into any coherent pattern. Some orbit clockwise, some orbit counterclockwise, some plunge straight through the core and swing back out in long elliptical loops. The result is a galaxy that looks less like a machine and more like a swarm, a cloud of stars held together by gravity with no underlying order to their motions. The stars in elliptical galaxies are old. Not just old in the sense that they have been around for a while, but old in the sense that they formed billions of years ago during the galaxy's youth and have been coasting ever since. The dominant stellar population in an elliptical is made up of red giants, low-mass stars that have exhausted the hydrogen in their cores and expanded into bloated shells of cooling gas. These stars glow a dull red or orange, nothing like the brilliant blue-white of the young massive stars that light up spiral arms. When you add up the light from billions of red giants, the galaxy as a whole takes on a reddish tint. Astronomers call this the red and dead paradigm. Red because the stars are old and cool. Dead because the galaxy is no longer forming new stars at any significant rate. It is not growing, it is not evolving, it is just sitting there, slowly dimming as its stars age and die one by one. The reason ellipticals do not form stars is simple. They do not have the raw materials. Star formation requires gas, specifically cold, dense clouds of hydrogen that can collapse under their own gravity and ignite fusion. Spiral galaxies have enormous reservoirs of gas scattered throughout their disks. Ellipticals do not. Most of the gas that was present when the elliptical formed has either been used up in past rounds of star formation or stripped away by environmental processes. What little gas remains is too hot and too diffuse to collapse. In a spiral galaxy, gas sits in a rotating disk where it can cool down, clump together, and form stars. In an elliptical, the gas is scattered throughout a three-dimensional volume with no organized rotation. It does not settle into a disk. It does not cool efficiently. It just sits there, heated by radiation from the stars and by any active galactic nucleus that might be lurking at the core. Without cold gas, there is no star formation. Without star formation, the galaxy cannot build new blue stars to replace the ones that die. The result is a galaxy that gets redder and dimmer over time, slowly fading as its stellar population ages. Elliptical galaxies come in a range of sizes, from massive giants containing trillions of stars down to dwarf ellipticals with only a few million. The local group does not have any massive ellipticals. The largest galaxies here are spirals, Andromeda and the Milky Way, and after them comes Triangulum. The ellipticals in the local group are all on the smaller end of the scale, either dwarf ellipticals or what astronomers call dwarf spheroidals, which are essentially ultra-faint ellipticals with so few stars that they are barely distinguishable from the noise in deep sky images. Despite being small and faint, these ellipticals are important because they are everywhere. The local group contains dozens of them, far outnumbering the spirals. They orbit the larger galaxies as satellites, drifting through the halos of Andromeda and the Milky Way, slowly losing stars to tidal stripping, slowly fading into the background. They are the forgotten majority, the galaxies nobody talks about because they do not do anything interesting. But they are the most common type of galaxy in the local group by number, and understanding how they got that way is essential to understanding how galaxies evolve. One of the most studied ellipticals in the local group is Messier 32, a compact elliptical galaxy sitting right next to Andromeda. It is so close to Andromeda that in most photographs it looks like a bright blob stuck to the edge of Andromeda's disk. The two galaxies are not just neighbors, they are interacting. Tidal forces from Andromeda are pulling on Messier 32, distorting its shape, stripping away its outer stars. Messier 32 is being eaten, slowly and methodically, by the larger galaxy it orbits. The process will take billions of years to complete, but the outcome is already clear. Messier 32 will eventually be torn apart, its stars scattered into Andromeda's halo, its core absorbed into the larger galaxy's bulge. For now, it is still recognizable as a separate galaxy, a smooth spheroidal structure with no disk, no spiral arms, no gas, no star formation, just old stars drifting in random orbits, glowing a faint reddish-orange against the backdrop of space. Messier 32 is tiny compared to Andromeda. Its diameter is only about 6,500 light-years, roughly 1/30th the size of Andromeda's visible disk. It contains somewhere between 2 and 3 billion stars, a respectable number for a dwarf elliptical, but a rounding error compared to Andromeda's trillion. Despite its small size, Messier 32 is unusually dense. The stars in its core are packed together much more tightly than the stars in a typical dwarf galaxy, which has led some astronomers to propose that Messier 32 is not a dwarf elliptical at all, but the stripped core of a much larger galaxy. The idea is that Messier 32 was once a normal spiral or elliptical galaxy with its own disk and halo, but when it wandered too close to Andromeda, tidal forces ripped away everything except the dense central core. What we see today is the leftover, the stubborn nucleus that survived the interaction while the rest of the galaxy was scattered into Andromeda's halo. If that model is correct, Messier 32 is not just a dwarf elliptical. It is a scar, the remnant of a much larger structure that lost a fight with a giant. Another elliptical in the local group is NGC 205, also orbiting Andromeda. NGC 205 is slightly larger than Messier 32, with a diameter of roughly 11,000 light-years and a population of a few billion stars. Like Messier 32, it is smooth, featureless, and dominated by old red stars. Unlike Messier 32, NGC 205 shows faint hints of recent star formation buried in its core. Observations from the Hubble Space Telescope have revealed small pockets of young blue stars near the center of the galaxy. Stars that could not be more than a few 100 million years old. That is unusual for an elliptical. Ellipticals are supposed to be dead, their star formation shut down billions of years ago. The presence of young stars in NGC 205 suggests the galaxy managed to hold on to a small reserve of gas, enough to trigger a brief burst of star formation relatively recently. It is not enough to change the overall character of the galaxy. NGC 205 is still red. It is still dominated by old stars. It is still an elliptical. But the young stars are there, sitting in the middle of a galaxy that should not have any, and their presence is a reminder that the boundaries between galaxy types are not as clean as the textbook definitions suggest. The formation of elliptical galaxies is one of the more violent processes in the universe. The standard model for how ellipticals form involves mergers, collisions between two or more galaxies that scramble their structures and mix their stars into a single chaotic blob. When two spiral galaxies collide, the disks do not survive. Tidal forces from the interaction pull stars and gas out of their organized orbits and fling them into new trajectories. The spiral arms get stretched, distorted, torn apart. Gas clouds that were drifting peacefully through the disk suddenly find themselves compressed by the gravity of the other galaxy, triggering massive bursts of star formation. The collision heats the gas to temperatures where it can no longer collapse, shutting down further star formation once the initial burst fades. The stars from both galaxies get mixed together, their orbits randomized, their coherent rotation destroyed. What emerges from the wreckage is an elliptical galaxy, a smooth, featureless distribution of stars with no disk, no spiral arms, no organized rotation, just a swarm of old stars drifting in random directions. This process has been observed in detail thanks to deep sky surveys that can catch galaxies in the act of merging. One of the most famous examples is the antennae galaxies, two spirals in the process of colliding about 60 million light-years from Earth. Hubble images of the antennae show long tidal tails of stars and gas streaming out from both galaxies, pulled out by the gravitational interaction. The cores of the two galaxies are glowing brightly with fresh star formation triggered by the compression of gas clouds during the collision. In a few 100 million years, the two galaxies will complete their merger, and what will remain is an elliptical galaxy. The disks will be gone. The spiral arms will be gone. The tidal tails will fade as the stars settle into stable orbits. What will be left is a red, smooth, featureless blob of old stars, indistinguishable from any other elliptical in the universe. The Milky Way and Andromeda are headed for the same fate. When the two galaxies collide in roughly 4.5 billion years, the result will be an elliptical galaxy, not a spiral, not a disk, an elliptical. The spiral arms that define both galaxies today will be destroyed during the merger. The disks will be scrambled. The stars will be flung into random orbits. The supermassive black holes at the centers of both galaxies will spiral inward and merge, releasing gravitational waves that ripple through space-time. Gas clouds will be compressed, triggering one final burst of star formation before the remaining gas is heated beyond the point where it can collapse. Once that burst fades, the merged galaxy will settle into its final form, a massive elliptical containing the combined stellar populations of both galaxies. Astronomers have already run the simulations. They have already named the result, Milkdromeda. A giant elliptical, smooth and red and dead, sitting at the center of what used to be the local group. Not all ellipticals form through major mergers. Some form through a slower process called harassment, where a smaller galaxy repeatedly passes close to a larger galaxy and gets distorted by tidal forces over billions of years. Each close passage strips away a bit more of the smaller galaxy's structure. The disk gets thickened. The spiral arms get disrupted. Gas gets pulled out and scattered. Eventually, after enough passes, the smaller galaxy loses its disk entirely and settles into an elliptical shape. This process is more common in dense galaxy clusters, where interactions are frequent and violent. In the local group, the environment is less crowded, so harassment is a slower process, but it still happens. Many of the dwarf ellipticals orbiting Andromeda and the Milky Way probably started out as dwarf spirals or irregular galaxies with some amount of gas and star formation. Over billions of years, repeated interactions with the larger galaxy they orbit stripped away their gas and disrupted their structure, transforming them into the smooth, red, featureless ellipticals we see today. The dwarf spheroidals in the local group are an extreme example of this process. These galaxies are so faint and so diffuse that they were not discovered until the late 20th century, when deep sky surveys finally became sensitive enough to detect them. They contain only a few 100,000 to a few million stars, making them among the least luminous galaxies known. Most of them have no gas and no star formation. They are entirely composed of old stars, the kind that formed more than 10 billion years ago and have been coasting ever since. The stars are so spread out that the galaxies barely qualify as structures. Their densities are so low that if you were somehow standing in the middle of one, you would not see a sky full of stars. You would see a normal-looking sky with maybe a few more faint stars than usual scattered around. The galaxy would be invisible to you because the stars are too far apart to create the kind of dense glow you see when you look at the Milky Way's band across the summer sky. Despite being faint and nearly empty. Dwarf spheroidals are important because they are dominated by dark matter. In a normal galaxy, the visible stars and gas account for a decent fraction of the total mass, maybe 10 to 20%. In a dwarf spheroidal, the visible stars are such a tiny fraction of the total mass that the galaxy is essentially a clump of dark matter with a few stars sprinkled in as an afterthought. Some dwarf spheroidals have mass-to-light ratios exceeding 100, meaning they contain 100 times more mass than you would expect based on the amount of light they emit. That mass is not coming from stars, it is not coming from gas. It is dark matter, and these galaxies are giving astronomers one of the cleanest laboratories available for studying how dark matter behaves on small scales. The stars are just tracers, marking the presence of the invisible scaffolding holding the galaxy together. One of the more puzzling questions about dwarf spheroidals is how they manage to form in the first place. Galaxies need gas to build stars, and stars are what make a galaxy visible. If a dwarf spheroidal has no gas, where did the stars come from? The answer is that the gas must have been stripped away after the stars formed, either by tidal forces from a larger galaxy or by a process called ram pressure stripping, where a galaxy moving through a hot intergalactic medium gets its gas blown off by the pressure of the surrounding plasma. Once the gas is gone, star formation stops. The existing stars age and redden. The galaxy fades. What remains is a faint, smooth, nearly invisible structure held together by dark matter. This process is common in galaxy clusters, where the intergalactic medium is hot and dense, but it can also happen in the local group if a dwarf galaxy passes close enough to Andromeda or the Milky Way to feel the effects of their hot halos. The Large and Small Magellanic Clouds, two of the most prominent satellite galaxies of the Milky Way, are currently irregular galaxies with active star formation. They are not ellipticals, but they will be. Both galaxies are losing gas as they orbit the Milky Way, stripped away by tidal forces and ram pressure. The gas is forming a stream called the Magellanic Stream, a long, thin trail of hydrogen that wraps around the Milky Way like a ribbon. That gas used to be inside the Magellanic Clouds, feeding star formation, building new generations of stars. Now it is gone, pulled out into intergalactic space, never to return. The Magellanic Clouds are still forming stars, still glowing brightly in ultraviolet and infrared, still looking like active, dynamic galaxies, but they are on borrowed time. In a few billion years, they will run out of gas. Star formation will shut down. The young blue stars will die and be replaced by nothing. The galaxies will redden, smooth out, and settle into the same kind of red and dead configuration that defines every other elliptical in the local group. They will become dwarf ellipticals, orbiting the Milky Way as faint, featureless ghosts of what they once were. Eventually, they might fall all the way in and be absorbed entirely, their stars scattered into the Milky Way's halo, their identities erased. Elliptical galaxies are not doomed to stay elliptical forever. If a large elliptical manages to capture a steady supply of gas, either by accreting it from the intergalactic medium or by cannibalizing a gas-rich dwarf galaxy, it can restart star formation and potentially rebuild a disk. The new disk would not look like the old one. The stars would be younger. The structure would be messier, but the galaxy would no longer be red and dead. It would have blue stars again, glowing regions of ionized hydrogen, spiral arms traced out by density waves. This process is rare, but it has been observed in a few systems where ellipticals seem to be in the process of transforming back into spirals. The universe does not move in one direction. Galaxies can evolve from spirals to ellipticals through mergers, and under the right conditions, they can evolve back. The red and dead paradigm is not absolute. Some ellipticals still have faint traces of star formation, pockets of young stars buried in their cores or scattered through their halos. NGC 205 is one example. There are others. These galaxies are not fully dead. They are more like embers, still glowing faintly, capable of flaring up briefly if they find a bit of fuel. But, for the most part, ellipticals are finished. They are the end state of galactic evolution in environments where gas is scarce and interactions are frequent. They are what happens when a galaxy runs out of the raw materials needed to stay alive, when all the gas has been used up or stripped away, when all the young stars have died and no new ones can form to replace them. They are graveyards, smooth and red and quiet, filled with the ghosts of stars that formed billions of years ago when the universe was young and gas was plentiful. In the local group, ellipticals do not dominate the way they do in massive galaxy clusters, where the most luminous galaxies are almost always giant ellipticals formed through repeated mergers. Here, the largest galaxies are spirals. The ellipticals are smaller, fainter, less prominent, but they are the majority by number. There are dozens of dwarf ellipticals and dwarf spheroidals orbiting Andromeda and the Milky Way, far outnumbering the handful of spirals. If you counted galaxies by mass, the spirals would win easily. If you counted them by number, the ellipticals would dominate. That tells you something about how galaxies populate the universe. The big ones are rare, the small ones are common. And the small ones, in most cases, are red and dead, stripped of their gas, shut down, drifting through the halos of larger galaxies, waiting for the slow grinding process of tidal forces to tear them apart completely. The story of ellipticals is a story of endings. They are what happens when a galaxy stops growing, stops forming stars, stops doing anything that would make it stand out against the background. They are the final resting place for stars that have outlived their galaxies, structures so smooth and featureless that they look less like objects and more like voids, dark patches against a darker sky. And yet they are not empty. They are full of stars, billions of them, each one a sun that once burned brightly and now drifts silently through space, held in place by gravity and dark matter, part of a structure that will persist for trillions of years until the stars themselves burn out and the galaxy fades into absolute darkness. But not every galaxy in the local group fits cleanly into the spiral or elliptical categories. Some galaxies sit in between, hybrids that have features of both types or neither. Some have disks but no spiral arms. Some have gas but no organized rotation. Some are so chaotic and irregular that they defy classification entirely. Those galaxies are next, and they represent the messiest, most unpredictable outcomes in the zoo of galaxy types. Galaxies that started as something else and got scrambled by interactions, collisions, or environmental effects. Galaxies that are still in the process of figuring out what they are going to become. Galaxies caught in between. The story of ellipticals is a story of endings. They are what happens when a galaxy stops growing, stops forming stars, stops doing anything that would make it stand out against the background. They are the final resting place for stars that have outlived their galaxies, structures so smooth and featureless that they look less like objects and more like voids, dark patches against a darker sky. But not every galaxy in the local group fits cleanly into the spiral or elliptical categories. Some galaxies sit in between, hybrids that have features of both types or neither. Some have disks but no spiral arms. Some have gas but no organized rotation. Some are so chaotic and irregular that they defy classification entirely. Those galaxies are next, and they represent the messiest, most unpredictable outcomes in the zoo of galaxy types. Galaxies that started as something else and got scrambled by interactions, collisions, or environmental effects. Galaxies that are still in the process of figuring out what they are going to become. Galaxies caught in between. Astronomers sorting galaxies into categories have always known the system is imperfect. Nature does not read the textbook. It does not care that we decided spiral galaxies should have arms and elliptical galaxies should be smooth. The universe produces objects that do not fit, and when you find enough of them, you have to either expand the classification system or admit that the boundaries between types are blurrier than you wanted to believe. In the early 20th century, Edwin Hubble tried to impose order on the chaos by creating his famous tuning fork diagram, a branching tree that sorted galaxies into spirals, ellipticals, and a third category he called lenticulars. The lenticulars were the awkward middle children, galaxies that looked like they should be spirals but were not quite spiral enough to qualify. They had disks, they had bulges, they did not have prominent spiral arms. Hubble put them at the junction of his tuning fork, sitting between the ellipticals and the spirals, and gave them the designation S0. The name stuck, the category stuck. And for decades, astronomers have been arguing about what lenticular galaxies actually are, how they formed, and whether they represent a stable evolutionary stage or just a galaxy caught in the middle of transforming from one type into another. A lenticular galaxy has a disk, that much is clear. The stars are not scattered randomly through a three-dimensional volume the way they are in an elliptical. They are flattened into a rotating structure, organized into coherent orbits around a central bulge. The disk is there. You can see it in edge-on views where the galaxy looks like a line stretched across the sky. You can measure it in face-on views where the galaxy looks like a smooth, glowing lens, which is where the term lenticular comes from. Lens-shaped, but the disk does not have spiral arms, or if it does, they are so faint and poorly defined that they barely register in photographs. There are no bright blue star-forming regions lighting up the outer disk. There are no prominent dust lanes tracing out the structure of the spiral. The galaxy looks smooth, almost featureless, the way an elliptical does. But it is clearly not an elliptical because the flattened disk structure is obvious. It is something else, something in between. The stars in a lenticular galaxy are mostly old. The dominant population is red giants and aging main sequence stars, the same kind of stars that dominate ellipticals. That tells you star formation in lenticulars shut down a long time ago, or at least slowed to a crawl. The galaxy is not building new generations of massive blue stars. It is coasting on the stars it made billions of years ago, slowly reddening as those stars age. The gas supply is low or non-existent. What little gas remains is too hot or too diffuse to collapse into new stars. The result is a galaxy that looks like a spiral in structure, but behaves like an elliptical in terms of its stellar population. It has the skeleton of a spiral, but the complexion of a graveyard. The question that has dogged astronomers for decades is how lenticulars form. Are they spirals that lost their spiral arms? Are they ellipticals that somehow rebuilt a disk? Are they a separate evolutionary path entirely, a third track that runs parallel to the other two? The most widely accepted explanation is that lenticulars are faded spirals. Galaxies that used to have spiral arms and active star formation, but lost the gas needed to keep the process running. Once the gas is gone, the spiral arms fade. The density waves that used to compress gas and trigger star formation keep running, but with no gas to light them up, the arms become invisible. The disk remains because the stars that were already in the disk do not disappear when the gas runs out. They keep orbiting. The structure persists. What you are left with is a smooth disk galaxy with no star formation and no visible spiral arms, a lenticular. Gas can be removed from a galaxy in several ways. The most common is ram pressure stripping, where a galaxy moving through a hot intergalactic medium gets its gas blown off by the pressure of the surrounding plasma. This process is extremely effective in dense galaxy clusters where the space between galaxies is filled with hot ionized gas. A spiral galaxy falling into a cluster at high speed can have its entire gas supply stripped away in less than 100 million years. The stars do not get stripped because they are too massive and too tightly bound to the galaxy's gravitational potential, but the gas is loosely bound and the pressure from the intergalactic medium is strong enough to blow it out of the disk entirely. Once the gas is gone, star formation stops. The spiral arms fade. The galaxy transitions into a lenticular. This process is so common in galaxy clusters that lenticulars make up a huge fraction of the galaxy population in those environments. They are less common in the local group because the space between galaxies here is less dense and the ram pressure is weaker, but the mechanism still works. Another way to remove gas from a spiral is through tidal interactions with a larger galaxy. When a smaller galaxy orbits a giant like Andromeda or the Milky Way, tidal forces pull on the gas more strongly than they pull on the stars. The gas gets stretched into long tidal tails and eventually stripped away entirely. The stars remain in the disk, but the gas is gone. Star formation shuts down. The galaxy fades from a spiral into a lenticular. This is probably the dominant mechanism for creating lenticulars in the local group, where most galaxies are satellites of one of the two giants. Over billions of years, repeated close passes to the host galaxy strip away the gas supply, and what was once a vibrant spiral becomes a smooth, featureless disk galaxy with no star formation and no visible structure. A third possibility is that some lenticulars are not faded spirals at all, but galaxies that formed differently from the start. In this model, lenticulars are what you get when a disk galaxy forms in an environment where the gas supply is cut off early, before the galaxy has a chance to develop strong spiral arms. The disk forms, the stars form. But the spiral structure never fully develops because the gas gets removed or exhausted before the density waves can carve out prominent arms. The galaxy settles into a smooth disk configuration and stays that way for billions of years. This model is less popular than the faded spiral idea, but it is still on the table. There is also a more exotic proposal that some lenticulars might be stripped or transformed ellipticals. If an elliptical galaxy somehow captures a supply of gas, either by accreting it from the intergalactic medium or by cannibalizing a gas-rich dwarf, the gas can settle into a rotating disk. The stars in the original elliptical are still moving in random orbits, but the new gas disk is organized and rotating coherently. If star formation in that disk is weak or short-lived, you end up with a galaxy that has an elliptical bulge and a smooth disk with no spiral arms, a lenticular. This scenario is speculative and probably rare, but it shows that the boundaries between galaxy types are not fixed. A galaxy can start as one type and transform into another, depending on its environment and its interactions with neighbors. The local group does not have many lenticulars. The dominant types here are spirals and ellipticals, with a large population of dwarf galaxies scattered between them. But there are a few candidates, galaxies that show disk structure but no clear spiral arms, that might be lenticulars or on their way to becoming lenticulars. The difficulty is that lenticulars are defined by what they lack rather than what they have. A spiral without spiral arms, a disk galaxy without star formation. The distinction between a faint spiral and a lenticular is not always clear, especially when you are looking at small, distant galaxies where the details are hard to resolve. Some of the dwarf galaxies orbiting Andromeda and the Milky Way might be lenticulars. Others might be faded irregulars or disrupted spirals. The classification depends on how you interpret the data, and different astronomers looking at the same galaxy can come to different conclusions. What makes lenticulars important is that they represent a transitional state. They are proof that galaxy morphology is not fixed. A galaxy can start as a spiral and end as a lenticular. It can start as a lenticular and end as an elliptical if it merges with another galaxy or loses its disk structure entirely. The categories we use to classify galaxies are useful for organizing the population, but they are snapshots of a continuous process. Galaxies are not locked into one type for their entire lives. They evolve, they interact, they change. Lenticulars are what you get when a spiral loses its gas but keeps its disk. They are the middle stage in a transformation that might eventually turn them into ellipticals, or they might stay lenticulars forever, coasting on the stars they already have until those stars dim and the galaxy fades into the background. Either way, they are reminders that the universe does not respect the boundaries we draw. And then there are the irregulars, galaxies that do not even try to fit into the classification system. No disk, no bulge, no spiral arms, no smooth elliptical distribution, just chaos. A clump of stars and gas with no consistent, well-defined shape, no organized rotation, no coherent structure. Irregular galaxies look like someone took a spiral galaxy, ripped it apart, stirred the pieces, and left the wreckage floating in space. They are messy, they are asymmetric, and yet they are some of the most active, vibrant star-forming galaxies in the local group. The best-known irregular galaxies in the local group are the Large and Small Magellanic Clouds, two dwarf galaxies visible from the southern hemisphere as bright smudges in the night sky. The Large Magellanic Cloud, or LMC, sits about 160,000 light-years from the Milky Way. The Small Magellanic Cloud, or SMC, is slightly farther out at roughly 200,000 light-years. Both galaxies are close enough that they dominate the southern sky when you are far from city lights, glowing with a faint diffuse light that looks nothing like the sharp point of a star or the smooth glow of a distant spiral. They look more like clouds, which is where the name comes from. For centuries, sailors in the southern hemisphere used them as navigational aids, calling them the Clouds of Magellan after the explorer Ferdinand Magellan, whose crew documented them during the first circumnavigation of the globe in the early 16th century. The name stuck, and modern astronomers kept it even after they realized the clouds were not clouds at all, but entire galaxies, separate structures orbiting the Milky Way. The LMC contains roughly 30 billion stars. The SMC has about 3 billion. Both numbers are tiny compared to the Milky Way's few hundred billion, but they are still enormous by any human standard. 30 billion suns, scattered across a volume tens of thousands of light-years wide, glowing with the light of ongoing star formation. The LMC is one of the most active star-forming galaxies in the local group. Its star formation rate is high enough that the galaxy is constantly lighting up with new blue stars, glowing hydrogen clouds, and supernova remnants left behind by massive stars that formed and died within the last few million years. The Tarantula Nebula, one of the largest and brightest star-forming regions known, sits inside the LMC. It spans roughly 1,000 light-years across and contains some of the most massive stars ever observed. Stars weighing more than 100 times the mass of the Sun, burning so hot and so fast that they will only live a few million years before going supernova. If the Tarantula Nebula were sitting where the Orion Nebula is, only about 1,300 light-years from Earth, it would cast shadows on the ground at night. It is that bright. The SMC is smaller and less active than the LMC, but it is still forming stars. Its irregular structure is even more pronounced. a chaotic distribution of stars and gas with no clear organization. Both galaxies are rich in gas, which is why they can sustain active star formation despite being relatively small. Gas is the fuel. As long as they have it, they can keep building new stars. The problem is they are losing it. Both the LMC and SMC are being tidally stripped by the Milky Way. As they orbit the larger galaxy, tidal forces pull gas out of their disks and scatter it into intergalactic space. That gas forms a structure called the Magellanic Stream, a long, thin trail of hydrogen that wraps around the Milky Way like a ribbon. The stream was first detected in radio observations in the 1970s, and it has since been mapped in detail. It stretches across more than 200 degrees of the sky, making it one of the largest coherent structures associated with the Milky Way. The gas in the stream used to be inside the Magellanic Clouds. Now it is gone, pulled out by gravity, never to return. The clouds are still forming stars, still glowing brightly, still looking alive, but they are on borrowed time. Eventually, they will run out of gas. Star formation will shut down. The galaxies will fade, and in a few billion years, they might fall all the way into the Milky Way and be absorbed entirely, their stars scattered into the Milky Way's halo, their identities erased. The irregular structure of the Magellanic Clouds is not random. It is a direct result of gravitational interactions. The two galaxies are not just orbiting the Milky Way, they are also interacting with each other. The LMC and SMC are gravitationally bound, and they influence each other's orbits and shapes. The SMC in particular has been heavily distorted by its interactions with the LMC. Observations show that the SMC is elongated, stretched along the line connecting it to the LMC, a clear sign that tidal forces are pulling it apart. The LMC has also been distorted, though to a lesser degree. Both galaxies show asymmetries in their gas distributions, with more gas on one side than the other, indicating that material is being pulled out preferentially in the direction of the gravitational pull. The result is a pair of galaxies that look nothing like the clean, organized spirals or smooth ellipticals you see elsewhere in the local group. They are messy, chaotic, and in the middle of being torn apart by the larger galaxy they orbit. This process of tidal disruption is one of the primary mechanisms for creating irregular galaxies. When a smaller galaxy passes close to a larger one, the tidal forces are stronger on the side of the smaller galaxy facing the larger one than on the far side. That difference in gravitational pull stretches the smaller galaxy, distorting its shape. If the smaller galaxy has a disk, the disk gets warped. If it has spiral arms, the arms get pulled out into long tidal tails. Gas clouds get compressed by the tidal forces, triggering bursts of star formation in the regions where the compression is strongest. The galaxy's structure gets scrambled. What was once a nice orderly spiral or elliptical becomes an irregular, a chaotic mess of stars and gas with no clear organization. The Magellanic Clouds are textbook examples of this process in action. They are irregular galaxies, not because they formed that way, but because they have been distorted by interactions with the Milky Way and with each other. Mergers can also create irregulars. When two small galaxies collide, the result is often not a clean merger that produces a single well-defined galaxy, but a chaotic intermediate stage where the two structures are tangled together, their stars and gas mixed, but not yet settled into a stable configuration. The galaxy spends millions or hundreds of millions of years in this irregular state before gravity pulls everything together into something more organized. During that time, it looks irregular, asymmetric, messy. Observations of the local universe show plenty of galaxies caught in this transitional phase, galaxies that are clearly in the process of merging but have not yet completed the process. They are irregular not because they are inherently chaotic, but because they are in the middle of a violent transformation that has not finished yet. The other reason irregulars exist is that some galaxies are just small. Dwarf irregular galaxies are common throughout the local group, small clumps of stars and gas with no clear structure because they do not have enough mass to organize themselves into a disk or a bulge. Gravity needs a certain amount of mass to impose order. Below that threshold, galaxies stay messy. They form stars, they have gas, they glow, but they do not develop coherent rotation or spiral arms or any of the features that define larger galaxies. They are what happens when you give gravity a small amount of mass to work with and let it run for billions of years. The result is a galaxy that looks more like a cloud than a structure, a diffuse clump of stars held together loosely by gravity and dark matter. Irregular galaxies are often gas-rich, which is one of the main reasons they can sustain active star formation. Spirals have gas, but much of it is tied up in the disk, distributed smoothly across the galaxy. In irregulars, the gas is clumpy, concentrated in dense clouds where star formation can ignite more easily. The lack of organized rotation means the gas does not settle into a stable disk. It just drifts, clumps, and occasionally collapses into stars when the density gets high enough. The result is a galaxy with patchy star formation, bright regions scattered across the structure wherever the gas happened to collapse. The Magellanic Clouds show this pattern clearly. Star formation is not evenly distributed across the galaxy. It is concentrated in specific regions, giant molecular clouds where the gas is dense enough to trigger collapse. Those regions light up with young blue stars and glowing hydrogen, while the rest of the galaxy stays relatively dark. The overall appearance is irregular not just in shape, but in brightness, a patchwork of glowing regions separated by darker areas with fewer stars. The role of gravitational tides in shaping irregular galaxies cannot be overstated. Tides are everywhere in the local group. Every satellite galaxy orbiting Andromeda or the Milky Way feels tidal forces. Every close encounter between two galaxies generates tides. Tides pull gas out of galaxies. Tides stretch galaxies into elongated shapes. Tides trigger star formation by compressing gas clouds. Tides are one of the primary engines of galaxy evolution, and irregulars are the clearest evidence of tides at work. When you see a galaxy with an irregular shape, you are seeing the fingerprints of a past or ongoing interaction. Something pulled on that galaxy hard enough to distort it, and the structure has not yet recovered. Not all irregulars stay irregular forever. Some of them eventually settle into more organized forms as the tidal distortions fade and gravity pulls the structure back into equilibrium. A galaxy that was irregular after a close encounter with a larger neighbor might eventually relax into a dwarf elliptical or a lenticular if it loses enough gas and its stars settle into stable orbits. The irregular phase is temporary, a snapshot of a galaxy in the middle of a transformation. Other irregulars stay irregular for billions of years, sustained by ongoing interactions or by their low mass, which prevents them from organizing into a more coherent structure. The LMC and SMC will probably not stay irregular forever. As they continue to lose gas to the Magellanic Stream and as they continue to interact with the Milky Way, they will eventually run out of fuel for star formation. The stars will age and redden. The chaotic structure will smooth out as the remaining stars settle into more stable orbits. In a few billion years, they might look more like dwarf ellipticals than irregulars, assuming they are not absorbed by the Milky Way entirely before that happens. The dynamic nature of galaxy morphology is one of the central lessons of modern astronomy. Galaxies are not static. They are not locked into one category for their entire lives. They evolve, they interact, they change. Spirals can become lenticulars if they lose their gas. Lenticulars can become ellipticals if they merge with other galaxies. Irregulars can become ellipticals if they lose their gas and settle down. Ellipticals can become spirals if they capture new gas and rebuild a disk, though that process is rare. The categories we use to classify galaxies are useful tools for organizing the population, but they are not rigid boxes. They are descriptions of what a galaxy looks like right now, at this moment, in the snapshot we are taking with our telescopes. Billions of years from now, that same galaxy might look completely different. The Magellanic Clouds are a perfect example of this dynamic evolution playing out in real time. They are irregular galaxies right now, chaotic and star-forming, rich in gas and glowing with young blue stars. But they are also being slowly destroyed by the Milky Way. Tidal forces are stripping their gas. The Magellanic Stream is the visible evidence of that process, a trail of hydrogen stretching across the sky like a scar. In a few billion years, the clouds will run out of gas. Star formation will stop. The galaxies will fade. They might become dwarf ellipticals. They might be absorbed entirely. Either way, the irregular structure we see today is temporary. It is a phase, a moment in a much longer story that stretches across billions of years, and that is the real point. Lenticulars and irregulars are reminders that galaxy evolution is messy. It is not a clean progression from one type to another. It is a tangle of interactions, mergers, gas stripping, star formation, tidal disruptions, and slow transformations that play out over timescales so long that no human will ever witness the full arc. We see snapshots. We see galaxies caught in the middle of changing from one thing into another. Lenticulars are spirals that lost their arms. Irregulars are galaxies that got scrambled by tides. Both are proof that the universe does not care about our classification schemes. It just keeps pulling galaxies together, tearing them apart, and building new structures from the wreckage. But there is one more category to cover before the full picture of the local group comes into focus. One more class of galaxies that outnumbers all the rest, but is so faint, so dim, so nearly invisible that most of them were not even discovered until the late 20th century. Galaxies that are little more than ghosts, faint smudges in the sky, barely distinguishable from noise. Galaxies dominated not by stars, but by dark matter, structures so diffuse that if you were standing in the middle of one, you would not even realize you were inside a galaxy at all. They are the dwarf spheroidals, and they are everywhere. Orbiting Andromeda, orbiting the Milky Way, drifting through the empty spaces in between, and understanding what they are means understanding the invisible scaffolding that holds the entire local group together. The story of lenticulars and irregulars is a story of galaxies caught in the middle of transformations they may or may not complete, structures that do not fit cleanly into the categories we built to organize them. Lenticulars have disks, but no spiral arms. Irregulars have chaos, but no coherent structure. Both are reminders that galaxy evolution is messy, that the universe does not respect the boundaries we draw. But there is one more category to cover before the full picture of the local group comes into focus. One more class of galaxies that outnumbers all the rest, but is so faint, so dim, so nearly invisible that most of them were not even discovered until the late 20th century. Galaxies that are little more than ghosts, faint smudges in the sky, barely distinguishable from noise. Galaxies dominated not by stars, but by dark matter, structures so diffuse that if you were standing in the middle of one, you would not even realize you were inside a galaxy at all. They are the dwarf spheroidals, and they are everywhere, orbiting Andromeda, orbiting the Milky Way, drifting through the empty spaces in between, and understanding what they are means understanding the invisible scaffolding that holds the entire local group together. Dwarf spheroidal galaxies are not impressive. They do not glow brightly in photographs. They do not have spectacular spiral arms or glowing star-forming regions. They do not dominate the sky or inspire awe when you point a telescope at them. What they do is hide. They hide so well that for most of human history, we did not know they existed. The first dwarf spheroidals were discovered in the 1930s and 40s when astronomers were conducting surveys of the Milky Way's halo and noticed faint smudges that did not quite fit the pattern of star clusters. The smudges were too large, too diffused, and too dim to be normal globular clusters. They were something else, something fainter. It took years of careful observation and analysis to confirm that these faint smudges were not clusters at all, but entire galaxies, separate structures with their own dark matter halos, their own stellar populations, their own gravitational identities. Galaxies so faint that if you were standing in the middle of one, the night sky would look almost completely normal. You would see a few more stars than usual scattered across the blackness, but not enough to create the kind of dense glow you see when you look at the Milky Way's band across the summer sky. The galaxy would be invisible to you because the stars are too far apart and too faint to create a coherent glow. Dwarf spheroidals are defined by what they lack. They do not have gas. They do not have ongoing star formation. They do not have bright young blue stars. What they have is a sparse population of old red stars scattered across a volume tens of thousands of light-years wide. The stars are so spread out that the average density inside a dwarf spheroidal is lower than the density of stars in the Milky Way's halo. These galaxies are not dense. They are not tightly bound. They are barely holding together. The only reason they exist as coherent structures at all is because they are embedded in enormous dark matter halos that outweigh the visible stars by factors of 10, 100, sometimes even 1,000. The stars are just tracers, faint markers that tell astronomers where the dark matter is. Strip away the dark matter, and the dwarf spheroidals would not survive. The stars would drift apart, the structure would dissolve, the galaxy would cease to exist. The faintness of dwarf spheroidals is extreme. Some of them emit less light than a single bright star. The faintest known dwarf spheroidals have luminosities measured in just a few thousand solar luminosities. For comparison, the Sun alone has a luminosity of 1 solar luminosity. That means the entire galaxy, with all its stars combined, is only a few thousand times brighter than the Sun. A single massive blue star in a spiral galaxy's disk can emit tens of thousands or even hundreds of thousands of solar luminosities. One star can outshine an entire dwarf spheroidal. That is how faint these galaxies are. And because they are so faint, detecting them requires extremely sensitive instruments and careful analysis of deep sky surveys. You cannot just point a telescope at the sky and spot a dwarf spheroidal. You have to look at the distribution of individual stars in a region, measure their positions and brightnesses, and use statistical techniques to determine whether those stars are part of a coherent structure or just random foreground stars scattered along the line of sight. It is painstaking work. Most dwarf spheroidals were not discovered until the 1980s and 90s, when digital sky surveys finally became sensitive enough to detect them, and even now, astronomers are still finding new ones. The current count of dwarf spheroidals in the local group is somewhere around 50 or 60, but that number keeps growing as surveys get deeper and more complete. The reason dwarf spheroidals matter, despite their faintness, is what they tell us about dark matter. Dark matter is the invisible substance that makes up most of the mass in every galaxy. It does not emit light, it does not absorb light, It does not interact with normal matter except through gravity. We only know it exists because of the way it pulls on the things we can see. Stars in the outer regions of spiral galaxies orbit faster than they should, based on the visible mass alone. Galaxy clusters hold together with far more gravitational pull than their visible galaxies can account for. The cosmic microwave background, the faint afterglow of the Big Bang, shows temperature fluctuations that only make sense if dark matter was present in the early universe to seed the formation of structure. Dark matter is everywhere. It outweighs normal matter by a factor of about 5 to 1. And yet we have never directly detected a single dark matter particle. Every piece of evidence for dark matter is indirect, inferred from the way gravity behaves on large scales. Dwarf spheroidals are some of the cleanest laboratories for studying dark matter because the visible stars are such a tiny fraction of the total mass. In a normal galaxy like the Milky Way or Andromeda, the visible stars and gas account for maybe 10 to 20% of the total mass. The rest is dark matter. In a dwarf spheroidal, the visible stars account for less than 1% of the total mass. In some of the faintest dwarf spheroidals, the visible stars are less than 0.1%. The mass-to-light ratio, the ratio of total mass to the amount of light emitted, is enormous. Some dwarf spheroidals have mass-to-light ratios exceeding 1,000, meaning they contain 1,000 times more mass than you would expect based on the amount of light they emit. That mass is not coming from stars. It is not coming from gas or dust or black holes. It is dark matter. Pure, invisible, gravitationally dominant dark matter. Astronomers can measure the mass of a dwarf spheroidal by studying the motions of the stars inside it. Stars in a galaxy orbit the center of mass, and the speed of those orbits depends on how much mass is present. If you measure the velocities of a large sample of stars in a dwarf spheroidal, you can calculate how much mass is needed to produce those velocities. The result is always the same. The mass inferred from the star velocities is far larger than the mass of the visible stars. The difference is dark matter. The dwarf spheroidal is sitting in a dark matter halo, and that halo is holding the galaxy together. Without the dark matter, the stars would be moving too fast to stay bound. They would drift apart, and the galaxy would dissolve. The fact that dwarf spheroidals exist at all is direct evidence that dark matter is real, that it is present in large quantities, and that it plays a fundamental role in holding galaxies together. One of the most famous dwarf spheroidals is the Sagittarius dwarf spheroidal galaxy, discovered in 1994. Sagittarius dwarf is being torn apart by the Milky Way right now. The galaxy orbits the Milky Way in a highly elliptical orbit, and every time it passes through the Milky Way's disk, tidal forces stretch it into a long, thin stream. Observations show that the stars from Sagittarius dwarf are scattered across a huge region of the sky, wrapped around the Milky Way like a ribbon. The galaxy's core is still intact, sitting on the far side of the Milky Way from Earth, but the outer parts have been completely shredded. Stars that used to be part of Sagittarius dwarf are now drifting through the Milky Way's halo, orphaned from the galaxy they came from. The process has been going on for billions of years, and it will continue until Sagittarius dwarf is completely destroyed. In a few billion more years, the galaxy will be gone. Its stars will be scattered into the Milky Way's halo, indistinguishable from the billions of other stars drifting through that region. The only evidence that Sagittarius dwarf ever existed will be the chemical signatures in the stars, the faint fingerprints that tell astronomers these stars came from somewhere else. Sagittarius dwarf is important because it is a clear example of how fragile dwarf spheroidals are. These galaxies do not have the mass or the gravitational binding energy to survive close encounters with larger galaxies. Tidal forces from the Milky Way or Andromeda are strong enough to rip them apart over relatively short timescales. The stars get pulled out into long tidal streams. The dark matter halo gets stretched and distorted. Eventually, the galaxy loses so much mass that it can no longer hold itself together, and it dissolves. This process is happening to dozens of dwarf spheroidals in the local group right now. They are being slowly eaten by the larger galaxies they orbit. The end is inevitable. Dwarf spheroidals are not permanent. They are transient structures, temporary clumps of stars and dark matter that will eventually be absorbed by the giants. Another example is the Canis Major dwarf, discovered in 2003. Canis Major is even more disrupted than Sagittarius dwarf. The galaxy sits close to the plane of the Milky Way's disk, and tidal forces have stretched it into a long stream that wraps around the galaxy. Observations of the region show an overdensity of stars, a clump of objects that appear to be part of a coherent structure rather than random foreground stars. The problem is that the region is crowded. The Milky Way's disk is full of stars, and distinguishing between stars that belong to Canis Major and stars that are just part of the Milky Way's disk is extremely difficult. Some astronomers are convinced that Canis Major is a real dwarf galaxy being torn apart by the Milky Way. Others are not convinced. They argue that the overdensity could be explained by other structures in the Milky Way's disk, such as spiral arms or fluctuations in the stellar population. The debate has not been fully resolved, and Canis Major remains one of the more controversial objects in the local group. Regardless of whether Canis Major is a real dwarf galaxy or a misidentified Milky Way structure, the fact that the debate exists at all highlights how difficult it is to study dwarf spheroidals. They are so faint and so diffuse that even identifying them as separate galaxies requires careful statistical analysis and multiple lines of evidence. The formation and survival of dwarf spheroidals is one of the more puzzling questions in galaxy evolution. These galaxies are extremely fragile. They have low masses, they have no gas, they have no ongoing star formation. They are sitting in the gravitational fields of much larger galaxies that are constantly pulling on them with tidal forces. By all rights, they should not exist. They should have been destroyed billions of years ago. The fact that they are still here, still recognizable as separate structures, tells you that something is protecting them, that something is dark matter. The dark matter halos surrounding dwarf spheroidals are much more extended and much more massive than the visible stars. The halo acts as a buffer, shielding the stars from the worst of the tidal forces. The outer parts of the halo get stripped away, but the core remains intact. As long as the dark matter halo is massive enough, the galaxy can survive repeated close passes to the host galaxy without being completely destroyed. This is why dwarf spheroidals are so valuable for studying dark matter. Their survival depends on the properties of their dark matter halos, and by studying how they are being torn apart, astronomers can learn about the distribution and behavior of dark matter on small scales. The high dark matter content of dwarf spheroidals also makes them key evidence for the existence of dark matter in the first place. When astronomers first started measuring the velocities of stars in these galaxies, the results were shocking. The stars were moving much faster than they should be based on the visible mass alone. The only way to explain the velocities was to assume that the galaxies contained enormous amounts of unseen mass. That unseen mass is dark matter. The same conclusion had already been reached for larger galaxies and galaxy clusters, but dwarf spheroidals provided some of the cleanest and most unambiguous evidence. In a large galaxy like the Milky Way, the situation is more complicated. The disk has gas, the bulge has stars, the halo has globular clusters. All of these components contribute to the total mass, and disentangling how much of that mass is visible and how much is dark matter requires detailed modeling and assumptions about the structure. In a dwarf spheroidal, the situation is simpler. There is no gas. There is almost no dust. The stars are all old and red, so there is no ongoing star formation to complicate the picture. The only thing contributing to the mass is the stars and the dark matter. Measure the star velocities, calculate the total mass, subtract the mass of the visible stars. What is left is dark matter. The calculation is clean. The conclusion is unambiguous. Dwarf spheroidals are dark matter-dominated structures, and their existence is one of the strongest pieces of evidence that dark matter is real. The number of dwarf spheroidals in the local group is much higher than the number of spirals or ellipticals. There are two large spirals, Andromeda and the Milky Way. There is one medium-sized spiral, Triangulum. There are a handful of smaller spirals, irregulars and lenticulars, and then there are dozens of dwarf spheroidals scattered throughout the halos of the two giants. If you count galaxies by number, dwarf spheroidals dominate. They are the most common type of galaxy in the local group by a wide margin. And yet most people have never heard of them because they are so faint and so unremarkable. They do not show up in popular astronomy books. They do not make it into the headlines. They are the forgotten majority, the galaxies nobody talks about because they do not do anything interesting. But they are the majority, and understanding them is essential to understanding how the local group works. The reason there are so many dwarf spheroidals is related to how structure forms in the universe. In the standard model of cosmology, large structures like galaxies form through a process called hierarchical assembly. Small clumps of dark matter collapse first, forming the seeds of the first galaxies. Those small clumps merge together to form larger clumps. The larger clumps merge to form even larger structures. Over billions of years, this process builds up the massive galaxies we see today, like Andromeda and the Milky Way. But not every small clump gets absorbed. Some of them survive as separate structures, orbiting the larger galaxy they are bound to. Those surviving clumps are dwarf spheroidals. They are the leftovers from the hierarchical assembly process, the small building blocks that never got fully incorporated into the larger structure. Every large galaxy has a retinue of dwarf satellites because every large galaxy formed by accreting smaller galaxies over billions of years. The dwarfs are the ones that survived long enough to still be recognizable as separate objects. The problem is that the standard model predicts there should be far more dwarf galaxies than we actually observe. Simulations of structure formation in a dark matter-dominated universe produce hundreds or even thousands of small dark matter halos orbiting each large galaxy. Observations show only a few dozen. The discrepancy is known as the missing satellites problem, and it has been one of the most debated issues in cosmology for the past 2 decades. There are several possible explanations. One is that many of the predicted dark matter halos never formed stars. They exist as invisible clumps of dark matter with no visible component, so we cannot detect them. Another possibility is that the smallest dark matter halos were destroyed by the radiation from the first stars, which heated the gas inside the halos and prevented it from collapsing to form new stars. A third possibility is that the simulations are wrong, that the properties of dark matter on small scales are different from what the simulations assume. The missing satellites problem is still open, and dwarf spheroidals are at the center of the debate. Understanding how many of them exist, how massive they are, and how they formed is crucial to testing the predictions of the standard model. The faintest dwarf spheroidals discovered in recent years are so dim that they challenge the definition of what a galaxy even is. Some of them contain only a few thousand stars, a few thousand. For comparison, a typical globular cluster, which is not a galaxy but a single bound cluster of stars, can contain hundreds of thousands or even millions of stars. The faintest dwarf spheroidals have fewer stars than many globular clusters. The difference is that globular clusters do not have dark matter halos. They are held together purely by the gravity of their visible stars. Dwarf spheroidals, no matter how faint, have dark matter. That is what makes them galaxies rather than clusters. The dark matter halo is the defining feature. Without it, the structure would not exist. The stars alone do not have enough mass to hold the system together. The dark matter is what makes a dwarf spheroidal a galaxy, and studying these ultra-faint systems is giving astronomers a window into the smallest scales where galaxies can form. Some astronomers have started calling the faintest dwarf spheroidals ultra-faint dwarfs to distinguish them from the slightly brighter classical dwarf spheroidals that were discovered decades ago. The ultra-faint dwarfs were only discovered in the last 20 years as digital sky surveys became deep enough to detect them. Surveys like the Sloan Digital Sky Survey, which mapped large swaths of the northern sky in unprecedented detail, revealed dozens of new dwarf galaxies that had been sitting in the Milky Way's halo all along, invisible to earlier surveys because they were too faint. Each new discovery added another data point to the population of dwarf spheroidals, and each one reinforced the conclusion that these galaxies are dominated by dark matter. The mass-to-light ratios of the ultra-faint dwarfs are among the highest measured for any galaxy, reaching values of several hundred or even 1,000 in some cases. They are the darkest galaxies in the universe, not because they absorb light, but because they emit so little light relative to their total mass. The chemical composition of stars in dwarf spheroidals also tells an interesting story. The stars in these galaxies are old, typically more than 10 billion years, which means they formed early in the history of the universe. But they are also metal poor, meaning they contain very low abundances of elements heavier than hydrogen and helium. Heavy elements, also called metals in astronomical terminology, are produced inside stars and released into the surrounding gas when those stars die in supernovae. Over time, the gas in a galaxy becomes more and more enriched with metals as successive generations of stars form, live, and die. Galaxies with active star formation over long periods build up high metal abundances. Dwarf spheroidals have low metal abundances because star formation shut down early. The galaxies formed their stars in a brief burst billions of years ago, and then the gas was stripped away or blown out before further generations of stars could form. The result is a stellar population that is old and metal poor, frozen in time, a snapshot of what the early universe looked like when the first galaxies were forming. Dwarf spheroidals are also useful for studying the early universe because their simplicity makes them easier to model than larger, more complex galaxies. A spiral galaxy like the Milky Way has a disk, a bulge, a halo, spiral arms, ongoing star formation, gas flows, interactions with satellites, and a supermassive black hole at the center. Modeling all of that requires sophisticated simulations that account for dozens of different physical processes. A dwarf spheroidal is much simpler. It has old stars, it has a dark matter halo. That is basically it. No gas, no star formation, no complex structure. Modeling a dwarf spheroidal is much more straightforward, and the results can be compared directly to observations without having to worry about all the complications that make larger galaxies so difficult to understand. That simplicity makes dwarf spheroidals valuable test cases for theories of galaxy formation and dark matter. The future of dwarf spheroidals in the local group is already written. They are being slowly destroyed by the larger galaxies they orbit. Tidal forces are pulling them apart, stripping away their outer stars, stretching them into long, thin streams. The process is slow, but it is inevitable. In a few billion years, most of the dwarf spheroidals currently orbiting Andromeda and the Milky Way will be gone. Their stars will be scattered into the halos of the larger galaxies, indistinguishable from the billions of other stars drifting through those regions. The dark matter halos will be disrupted and absorbed into the larger dark matter halos surrounding Andromeda and the Milky Way. The galaxies will cease to exist as separate structures. The only evidence they were ever there will be the tidal streams, the faint trails of stars marking the paths the galaxies took as they spiraled inward and were torn apart. Astronomers are already mapping those streams. The Sagittarius stream is the most prominent, but there are others. Each stream is the ghost of a dwarf galaxy that fell into the Milky Way and did not survive. And that is the story of dwarf spheroidals. Faint, fragile, nearly invisible, and yet essential to understanding how galaxies form and how dark matter behaves. They are the most numerous galaxies in the local group, the forgotten majority that outnumbers the spirals and ellipticals by a wide margin. They are dominated by dark matter to a degree that makes them some of the strongest evidence we have that dark matter is real. They are being slowly destroyed by the larger galaxies they orbit, torn apart by tidal forces, their stars scattered into the halos of giants. They are windows into the early universe, relics of the first generation of galaxies that formed more than 10 billion years ago. They are laboratories for testing theories of structure formation and dark matter on the smallest scales where galaxies can exist. And they are proof that size is not the only thing that matters. A galaxy with only a few thousand stars can tell you more about the fundamental structure of the universe than a galaxy with 1 trillion stars, if you know how to read the signal. But dwarf spheroidals are not isolated objects drifting through space on their own. They are part of a larger system, a gravitationally bound cluster of galaxies that includes spirals, ellipticals, lenticulars, irregulars, and dozens of dwarf spheroidals, all orbiting, interacting, merging, and slowly transforming over billions of years. That system is the local group, and understanding how all of these galaxies fit together, how they influence each other, how they formed, and where they are going is the next step. The local group is not just a collection of galaxies sitting near each other by coincidence. It is a cosmic family, an interconnected web of structures held together by gravity, shaped by billions of years of interactions and heading toward a future that is already written in the trajectories and the math. Dwarf spheroidals are not isolated objects drifting through space on their own. They are part of a larger system, a gravitationally bound cluster of galaxies that includes spirals, ellipticals, lenticulars, irregulars, and dozens of dwarf spheroidals all orbiting, interacting, merging, and slowly transforming over billions of years. That system is the local group, and understanding how all of these galaxies fit together, how they influence each other, how they formed, and where they are going is the next step. The local group is not just a collection of galaxies sitting near each other by coincidence. It is a cosmic family, an interconnected web of structures held together by gravity, shaped by billions of years of interactions, and heading toward a future that is already written in the trajectories and the math. The local group is the name astronomers give to the cluster of galaxies that contains the Milky Way. It is not a particularly large cluster. It is not the richest or the most massive. It is not sitting at the center of anything important in the grand scheme of the universe, but it is ours. It is the neighborhood we live in, the gravitational bubble that holds together everything close enough to call nearby. The boundary of the local group is fuzzy, defined not by a sharp edge, but by the point where the mutual gravity of the member galaxies stops being strong enough to hold things together against the expansion of the universe. Different studies place that boundary at different distances. but most estimates land somewhere around 10 million light-years across. That is the diameter. If you drew a sphere centered on the local group's center of mass, everything within roughly 5 million light-years in any direction would be part of the family. Inside that sphere, depending on whose count you trust, there are somewhere between 80 and 130 galaxies. The discrepancy is not because astronomers are bad at counting. It is because the smallest and faintest galaxies are extremely difficult to detect, and the definition of what counts as a galaxy versus a dissolving tidal stream or a globular cluster is not always clear. Some surveys are more conservative and only count galaxies they are confident are real, distinct structures. Other surveys are more inclusive and count every faint overdensity of stars that might be a galaxy. The number keeps growing as deeper sky surveys find more ultra-faint dwarfs hiding in the noise. A decade ago, the membership of the local group was thought to be around 50 galaxies. Now it is closer to 100, and that number will probably keep climbing as instruments get more sensitive. The point is that the local group is not a small, sparse collection of a few bright galaxies. It is crowded with dozens of small, faint, nearly invisible structures scattered throughout the volume, most of them orbiting one of the two giants. And that is the first important thing to understand about the local group. It is not a democracy, it is a hierarchy. Two galaxies dominate the mass, the gravitational pull, and the entire structure of the cluster, Andromeda and the Milky Way. Everything else is responding to their gravity. The smaller galaxies orbit them, merge with them, get torn apart by them, or drift in the spaces between them. Triangulum is the third largest, but it is still dwarfed by the two giants. After Triangulum, the rest of the membership drops off sharply in size and mass. There are a few dwarf irregulars, like the large and small Magellanic Clouds. There are a handful of dwarf ellipticals and lenticulars. And then there are the dozens of dwarf spheroidals, faint smudges barely distinguishable from the background, held together by dark matter halos that outweigh their visible stars by factors of 100 or more. The mass distribution in the local group is lopsided. Andromeda and the Milky Way together account for the vast majority of the total mass. Everything else combined is a rounding error. The total mass of the local group is difficult to measure precisely because most of the mass is dark matter, and dark matter does not glow. You cannot just add up the light from all the galaxies and multiply by some factor to get the total mass. You have to measure the motions of the galaxies, the velocities at which they are moving relative to each other, and use those velocities to infer how much mass is present. The calculation depends on assumptions about how the galaxies are distributed, how much dark matter is present, and whether the group is in a stable configuration or still evolving. Current estimates put the total mass of the local group at somewhere between 2 trillion and 5 trillion solar masses. That is an enormous range, and the uncertainty reflects how hard it is to weigh a cluster of galaxies from the inside. We are sitting in one of the member galaxies, looking out at the others, trying to figure out how much they weigh and how fast they are moving based on measurements that are noisy and incomplete. It is like trying to weigh a group of people by watching how fast they walk past each other without ever being able to put any of them on a scale. The center of mass of the local group is not the Milky Way. It is not Andromeda either. It is somewhere in between. That might sound obvious, but it is worth pausing on because most people instinctively assume the center of mass would be at the location of the largest galaxy. It is not. The center of mass is the balance point, the spot where the combined gravitational pull of all the galaxies in the group cancels out. If you could somehow remove all the galaxies except for their gravity and look at where the net gravitational field pointed to zero, that spot would be the center of mass. NASA's Imagine the Universe resource describes the center as somewhere between the Milky Way and Andromeda, which is accurate but vague. More precise estimates place it about 450 kiloparsecs, roughly 1.5 million light-years, from the Milky Way in the direction of Andromeda. That puts it closer to Andromeda than to us, which makes sense because Andromeda is more massive. The more massive object pulls the center of mass toward itself. The Milky Way and Andromeda are not sitting still relative to that center. They are orbiting it, slowly spiraling inward as their mutual gravity pulls them closer together. That inward spiral is one of the defining features of the local group's dynamics. Andromeda and the Milky Way are not moving away from each other the way most galaxies in the universe are because of cosmic expansion. They are moving toward each other at roughly 110 to 123 kilometers per second, depending on whose measurement you use. That is fast by human standards. It is slow by cosmic standards. At that speed, the two galaxies are closing the gap by about 3.5 billion kilometers every year. That sounds like a lot, until you remember that the current distance between the Milky Way and Andromeda is about 2.5 million light-years, which translates to roughly 24 quintillion kilometers. They have a long way to go, but the trajectory is clear. The two galaxies are falling toward each other, and barring some unexpected intervention, they will collide in roughly 3 to 4 billion years. When they do, the collision will not be a quick event. It will take billions of years to complete, as the galaxies pass through each other multiple times, their gravity pulling and stretching and warping both structures, eventually merging into a single massive elliptical galaxy that astronomers have already nicknamed Milkomeda or Milkdromeda, depending on who you ask. The name is not official. It is just the nickname that stuck, because it is the only name that makes sense. The motion of Andromeda and the Milky Way toward each other is driven by gravity, the same force that holds the entire local group together. Gravity does not care about cosmic expansion. On small scales, scales smaller than a few 100 million light-years, the gravitational pull between nearby objects is strong enough to overcome the expansion of space. That is why galaxies in clusters stay together. That is why the local group exists as a bound structure. The expansion of the universe is pulling distant galaxy clusters away from us, stretching the space between them. But inside the local group, gravity wins. The galaxies here are locked together, orbiting their common center of mass, interacting with each other, slowly merging and transforming. The local group is not expanding, it is contracting. The member galaxies are slowly falling inward, pulled by the gravity of Andromeda and the Milky Way, and in a few billion years, the structure will look completely different. The smaller galaxies in the local group are caught in this gravitational dance. Every dwarf spheroidal orbiting the Milky Way or Andromeda is slowly being pulled inward, losing stars to tidal stripping, shedding gas, fading. The Magellanic Clouds are losing gas to the Magellanic Stream, a long, thin trail of hydrogen stretching across the sky. Sagittarius Dwarf is being torn apart right now, its stars scattered into the Milky Way's halo. Messier 32, the compact elliptical orbiting Andromeda, is being eaten by the larger galaxy it circles. These interactions are not rare, they are the norm. The local group is a violent place on timescales long enough to matter, and the smaller galaxies are the ones paying the price. They are being absorbed, shredded, erased. In a few billion years, most of the dwarf galaxies currently orbiting Andromeda and the Milky Way will be gone. Their stars will be scattered into the halos of the giants. Their dark matter halos will be absorbed into the larger dark matter structures. The only evidence they existed will be the tidal streams, faint trails of stars marking the paths the galaxies took as they spiraled inward. The process of accretion is one of the key mechanisms driving galaxy evolution in the local group and everywhere else in the universe. Accretion is just a polite word for eating. Large galaxies grow by accreting smaller galaxies, pulling them in, tearing them apart, and incorporating their stars and gas into the larger structure. The Milky Way has done this dozens of times over its history. The stars in the Milky Way's halo, the diffuse cloud of old stars surrounding the disk, did not all form in the Milky Way. Many of them came from dwarf galaxies that fell in billions of years ago and were torn apart by tidal forces. The chemical signatures in those stars, the abundances of different elements, tell astronomers which stars came from which galaxies. By mapping those signatures, astronomers can reconstruct the accretion history of the Milky Way, piecing together the story of how the galaxy grew over time by eating its neighbors. Andromeda has a similar history. The stars in its halo came from disrupted satellites, smaller galaxies that got too close and did not survive. Every large galaxy in the universe has been built through this process. Hierarchical assembly, the gradual accumulation of smaller structures into larger ones, is the way galaxies grow. The local group is a snapshot of that process in action. But the local group is not an isolated island. It sits inside a much larger structure called the local sheet, which itself is part of the Virgo supercluster, an enormous collection of galaxy groups and clusters spanning more than 100 million light-years. The local group is just one small node in that web, a minor cluster sitting on the outskirts of the Virgo cluster, the massive collection of galaxies that dominates the gravitational landscape of this region of the universe. The Virgo cluster contains more than 1,000 galaxies, far more than the local group, and its total mass is estimated at roughly 1,000 trillion solar masses, 2 orders of magnitude larger than the local group. The Virgo cluster is the gravitational anchor for everything in this corner of the universe. The local group is falling toward it, pulled by the cluster's enormous mass. The motion is slow, only a few hundred kilometers per second, but it is steady. Over hundreds of billions of years, the local group will eventually merge with the Virgo cluster, and the galaxies here will become part of that much larger structure. By that time, the Milky Way and Andromeda will have already merged into Milkdromeda, so it will be a single massive elliptical galaxy falling into Virgo rather than 2 separate spirals. The details are hard to predict because the timescales are so long and the uncertainties in the measurements are so large. But the broad picture is clear. The local group is not a permanent structure. It is a temporary phase in a much longer process of hierarchical assembly that will eventually incorporate everything here into larger and larger structures. The gravitational interactions within the local group are more complicated than just the 2 giants pulling on each other. Every galaxy in the group pulls on every other galaxy. The forces are weak for the smallest dwarfs, but they are not zero. Triangulum, the 3rd largest galaxy in the group, is gravitationally interacting with Andromeda and possibly with the Milky Way as well. The orbit of Triangulum is still being debated. Some models suggest it is bound to Andromeda, orbiting the larger galaxy the way the Magellanic Clouds orbit the Milky Way. Other models suggest it is on a long elliptical orbit around the combined Andromeda and Milky Way system, or that it is passing through the local group on a trajectory that will take it somewhere else entirely. The data are not yet good enough to settle the question definitively. The proper motion of Triangulum, the sideways component of its velocity across the sky, is difficult to measure because the galaxy is so far away. Even the most precise instruments struggle to detect motion at that distance over the timescales we can observe. The answer will come eventually as more data accumulate, but for now Triangulum's fate is uncertain. It might fall into Andromeda and be absorbed. It might survive the merger between Andromeda and the Milky Way and remain as a satellite of the resulting elliptical. Or it might be flung out into intergalactic space entirely, ejected from the local group by the gravitational chaos of the collision. All three outcomes are possible, and which one happens depends on details we do not yet know. The smaller dwarf galaxies are also interacting with each other, though the interactions are weaker because their masses are so low. The large and small Magellanic Clouds are gravitationally bound to each other, and their mutual interactions have distorted both galaxies. The SMC has been stretched by the LMC's gravity, elongated along the line connecting the two galaxies. The LMC has been disturbed as well, though to a lesser degree. Both galaxies are also interacting with the Milky Way, and the combination of those interactions is what created the Magellanic Stream, the long trail of hydrogen gas stripped from the clouds and scattered across the sky. The stream is one of the largest structures associated with the Milky Way, stretching more than 200 degrees across the celestial sphere. It is visible in radio observations, a faint glow of neutral hydrogen emitting at 21 centimeters. The gas in the stream is moving away from the clouds, pulled out by tidal forces, and it will eventually fall into the Milky Way and be incorporated into the disk. In a few billion years, that gas will collapse and form new stars, and those stars will carry the chemical signatures of the Magellanic Clouds, a faint fingerprint left behind by galaxies that no longer exist. The ongoing dance of accretion and stripping within the local group is not just a curiosity. It is a fundamental process shaping the structure and evolution of every galaxy in the cluster. The Milky Way is actively accreting material from its satellites right now. Gas from the Magellanic Stream is falling into the disk. Stars from Sagittarius Dwarf are being absorbed into the halo. Tidal streams from other disrupted dwarfs are scattered throughout the Milky Way's outer regions, each one a scar marking the death of a smaller galaxy. The same process is happening around Andromeda. Messier 32 is being stripped. NGC 205 is losing stars to tidal forces. Dozens of faint dwarf spheroidals are slowly dissolving, their stars pulled out into long, thin streams. The rate of accretion is not constant. It depends on how close the satellites are, how massive they are, and how their orbits bring them into the tidal fields of the larger galaxies. Some satellites survive for billions of years, drifting through the halo on wide orbits that keep them far from the most destructive tidal forces. Others fall in quickly, torn apart within a few 100 million years. The outcome depends on the details, and those details are different for every satellite. The local group's membership is not static. New galaxies are being discovered every few years as sky surveys get deeper and more sensitive. Some of those new discoveries are real galaxies, faint dwarf spheroidals that were always there but too dim to detect with earlier instruments. Others are marginal cases, overdensities of stars that might be galaxies or might be tidal streams from galaxies that were already destroyed. The classification is not always clear. A dissolving dwarf spheroidal looks a lot like a tidal stream, and distinguishing between the two requires careful analysis of the positions, velocities, and chemical abundances of individual stars. The boundary between a galaxy and a stream is fuzzy, and some objects sit right on that boundary. Are they galaxies in the process of being destroyed, or are they streams from galaxies that were destroyed long ago? The answer depends on how you define a galaxy, and not everyone agrees on the definition. The total number of galaxies in the local group is also uncertain because some galaxies are hidden by the Milky Way itself. The plane of the Milky Way's disk is full of stars and dust, and anything sitting behind that plane is difficult or impossible to see. Astronomers call this region the zone of avoidance, a band stretching across the sky where observations are blocked by the Milky Way's material. Galaxies sitting in the zone of avoidance are invisible to optical telescopes. and even infrared and radio observations struggle to detect them through the clutter. There could be dozens of dwarf galaxies sitting in the zone of avoidance that we have not found yet because we cannot see through the Milky Way's disk. Surveys using infrared and radio wavelengths are slowly mapping that region, and new discoveries are being made every few years. Each new galaxy adds to the census of the local group and fills in another piece of the picture. The mass estimates for the local group depend heavily on assumptions about how much dark matter is present. The visible galaxies, the stars and gas we can actually see, account for only a small fraction of the total mass. The rest is dark matter, and the amount of dark matter determines how strong the gravitational pull is and how fast the galaxies are moving. Different models make different assumptions about the dark matter distribution, and those assumptions lead to different mass estimates. Some models assume the dark matter is distributed smoothly throughout the local group, following the same general pattern as the visible galaxies. Other models assume the dark matter is clumped into halos around each galaxy, with less material in the spaces between. The truth is probably somewhere in between, but without a direct way to measure dark matter, the models rely on indirect evidence like galaxy velocities and rotation curves. The uncertainties are large, and that is why the total mass estimate for the local group has such a wide range. 2 trillion solar masses is the lower end, 5 trillion is the upper end. The real value is somewhere in that range, and pinning it down more precisely will require better measurements of galaxy distances and velocities. The shape of the local group is also uncertain. If you plotted the positions of all the galaxies in 3 dimensions, would they form a sphere, an ellipse, a flattened disk, or some irregular blob? The answer is unclear, because measuring the 3-dimensional positions of galaxies is difficult. We can measure distances to nearby galaxies using techniques like Cepheid variables and the tip of the red giant branch, but those measurements have uncertainties, especially for the faintest dwarfs. The result is a fuzzy picture where the exact positions of many galaxies are not known precisely enough to map the overall shape. Most estimates suggest the local group is roughly spherical or slightly elongated, stretched along the line connecting the Milky Way and Andromeda. That makes sense because those are the 2 dominant masses, and everything else is responding to their gravity. The smaller galaxies are scattered throughout the volume, some clustered near the giants, others drifting in the spaces between. The distribution is not uniform. There are regions with higher concentrations of dwarfs and regions that are relatively empty. The pattern reflects the history of how the group formed, the mergers and interactions that shaped the structure over billions of years. The local group is also defined by what it is not. It is not a rich galaxy cluster like Virgo or Coma, packed with thousands of galaxies and dominated by massive ellipticals formed through repeated mergers. It is not a loose collection of galaxies drifting apart from each other, unbound by gravity. It is a small, compact cluster with just 2 large spirals, a handful of smaller galaxies, and dozens of faint dwarfs. The environment is relatively quiet compared to the dense centers of massive clusters where galaxies collide frequently, and RAM pressure stripping is so strong it can remove all the gas from a spiral galaxy in less than 100 million years. The local group is calm. Interactions happen, but they are slow and gentle compared to the violence in richer clusters. That calm environment is part of why spiral galaxies like the Milky Way and Andromeda still exist here. In a dense cluster, spirals get turned into lenticulars or ellipticals through gas stripping and mergers. In the local group, there is enough space and enough time for spirals to survive and evolve more slowly. The future of the local group is already written in the trajectories and the math. The Milky Way and Andromeda will merge. The smaller galaxies will fall in or be ejected. Triangulum will either be absorbed or flung out. The dwarf spheroidals will be torn apart and their stars scattered into the halos of the giants. In 4 or 5 billion years, the local group as it exists today will be gone, replaced by a single massive elliptical galaxy surrounded by a few surviving satellites and a lot of empty space. The merger will take billions of years to complete, long enough that the process will play out over timescales no human civilization could ever witness in full. But the outcome is clear. The two giants are falling toward each other, and there is no force strong enough to stop them. Gravity does not negotiate. The collision is inevitable. The local group is a temporary structure, a snapshot of a process that has been running for billions of years and will continue for billions more. And yet, even knowing that, even understanding that the structure is temporary and doomed to merge, the local group is still our home. It is the cluster we live in, the neighborhood our galaxy belongs to, the family of galaxies bound together by gravity and history. Every galaxy in the local group has a story. Andromeda, the giant, the largest structure in the cluster, moving closer every second. The Milky Way, our home, the second largest, orbiting the common center of mass. Triangulum, the third member, caught in the gravitational dance, its fate uncertain. The Magellanic Clouds, irregulars rich in gas and star formation, slowly being torn apart. The dozens of dwarf spheroidals, faint ghosts dominated by dark matter, the forgotten majority, all of them connected, all of them influencing each other, all of them part of a single system held together by the invisible pull of gravity. Understanding the local group means understanding that galaxies are not isolated islands drifting alone through space. They are part of systems, clusters, families. They interact, they merge, they transform, and the systems themselves are not permanent. They are phases in a longer process of hierarchical assembly that has been running since the first galaxies formed more than 13 billion years ago and will continue for trillions of years into the future. The local group is one chapter in that story, a small cluster of galaxies in an unremarkable corner of the universe, noteworthy only because we happen to live here, but noteworthy enough because this is where we are. This is the family we belong to. This is the dance we are part of. And understanding the local group, understanding how all these galaxies fit together and where they are going, is the first step toward understanding the larger structures beyond it, the superclusters and voids and filaments that make up the cosmic web. But before we zoom out to those larger scales, there is one more piece of the puzzle to consider. The local group is not just a collection of points in space, bright dots scattered across the sky that you can count and catalog and measure. It is a collection of shapes, structures, volumes. Each galaxy has a size, a mass, a form. And the way we talk about scale, the way we picture distance and size and structure in the universe, often flattens everything into points and numbers. We lose the sense of what these objects actually are. Andromeda is not a point 2.5 million light-years away. It is a structure 220,000 light-years across, a trillion stars held together by gravity and dark matter, a volume so large that light takes hundreds of thousands of years to cross it. The local group is not a list of 80 galaxies. It is a web of structures spanning 10 million light-years, each one a distinct shape with its own history and its own future. Understanding scale means understanding shape, not just distance. It means seeing galaxies as volumes, not points. And that shift in perspective changes everything about how we picture the universe and our place in it. Understanding the local group means understanding that galaxies are not isolated islands drifting alone through space. They are part of systems, clusters, families. They interact, they merge, they transform, and the systems themselves are not permanent. They are phases in a longer process of hierarchical assembly that has been running since the first galaxies formed more than 13 billion years ago and will continue for trillions of years into the future. The local group is one chapter in that story, a small cluster of galaxies in an unremarkable corner of the universe, noteworthy only because we happen to live here, but noteworthy enough because this is where we are. This is the family we belong to. This is the dance we are part of. And understanding the local group, understanding how all these galaxies fit together and where they are going, is the first step toward understanding the larger structures beyond it, the superclusters and voids and filaments that make up the cosmic web. But there is a problem with the way we have been trained to think about galaxies. Not a problem with the science, a problem with the mental picture. When you say the word galaxy, most people picture a point, a bright dot on a star chart, a smudge in a photograph, a distance measurement, 2.5 million light-years away, as if that number fully describes the object. It does not. A galaxy is not a point. It is not a distance. It is a shape, a volume, a structure that occupies space in 3 dimensions, that has width and depth and extent, that stretches across hundreds of thousands or even millions of light years. And until you shift your mental model from points to shapes, from distances to volumes, you cannot actually understand what scale means in the universe. You are just shuffling numbers around, comparing one incomprehensibly large figure to another, and none of it sticks because your brain has nothing to anchor it to. The shift from thinking about galaxies as points of light to thinking about them as 3-dimensional structures is not a minor adjustment. It changes everything about how you picture the universe and your place in it. Start with Andromeda, because Andromeda is the clearest example of this perceptual gap. When you look up on a clear autumn night and see that faint smudge of light in the constellation Andromeda, your eyes are telling you the galaxy is small. A fuzzy patch, barely wider than a star. Easy to miss if you do not know exactly where to look. That is the lie your senses are selling you. The truth is that Andromeda, if your eyes were sensitive enough to detect its full extent, would appear roughly 3 degrees across in the sky. That is 6 times wider than the full moon. 6 times. The object you are casually glancing past on your way to find something more interesting is actually dominating a massive section of the sky. You just cannot see most of it because the outer regions of the galaxy are too faint for human eyes to detect without long exposure photography or sensitive instruments. But the structure is there, all of it. A disk of stars and gas spanning 220,000 light-years, roughly twice the diameter of the Milky Way's visible disk. A stellar halo extending out to 500,000 light-years, filled with old red stars and the remnants of Galaxies Andromeda, cannibalized billions of years ago. A gaseous halo reaching at least 1.3 million light-years from the center, a diffuse cloud of hot ionized gas surrounding the entire structure like an atmosphere. That is the full extent of Andromeda, not a 2.5 million light-years away. A volume, a shape, a structure so large that light itself takes more than 200,000 years to cross from one side of the visible disk to the other. Now picture that same structure moving, because it is. Andromeda is not sitting still in space. It is falling toward the Milky Way at roughly 110 kilometers per second. Every second, the gap between the 2 galaxies closes by 110 kilometers. In the time it took you to read that sentence, Andromeda got several hundred kilometers closer. By tomorrow, millions of kilometers closer. By next year, billions. The collision is not a distant abstract possibility, it is scheduled. The math has been done, the trajectories have been mapped. In roughly 4.5 billion years, give or take a few 100 million depending on the model. Andromeda and the Milky Way are going to collide, and when they do, the merger will not be a quick event. It will take billions of years to complete as the two galaxies pass through each other multiple times, their gravity pulling and stretching and warping both structures. Stars will be flung out into new orbits. Gas clouds will compress and ignite, triggering massive waves of star formation. The supermassive black holes at the centers of both galaxies will spiral inward over millions of years and eventually merge into a single, even larger monster. The process will take so long that no human civilization could ever witness the full arc, but the outcome is already clear. The two galaxies will become one. The spiral arms will be destroyed. The disks will be scrambled. What emerges will be a massive elliptical galaxy, smooth and red and dead, a swarm of old stars orbiting a central core in random directions. The age of spirals in the local group will be over. That future is locked in, written into the trajectories and the gravitational equations. But even now, even before the collision begins in earnest, the scale of what is happening is almost impossible to hold in your head. Two structures, each one hundreds of thousands of light years across, each one containing hundreds of billions or trillions of stars, each one wrapped in a dark matter halo that outweighs all the visible matter by a factor of 5 or more, falling toward each other across a gulf of 2.5 million light years. Those are not points, those are not dots on a map, those are volumes, shapes, structures so large that the entire solar system, the sun and all its planets out to the edge of the Oort cloud would fit inside the central bulge of either galaxy with room to spare. And yet, when you look at a diagram of the local group, a sketch showing the positions of the member galaxies, Andromeda and the Milky Way are drawn as circles or ellipses, abstract symbols representing objects whose true scale is flattened into something that fits on a page. The diagram is useful. It shows the relative positions, the distances, the orbital paths. But it lies about the most important thing, which is that these are not symbols. They are physical structures occupying enormous volumes of space, and understanding their scale means understanding their shapes, not just their distances. The same applies to every other galaxy in the local group. Triangulum, the third largest member, is not a faint smudge sitting 3 million light-years away. It is a spiral galaxy 50 to 60,000 light-years across, containing 40 billion stars wrapped in a dark matter halo that holds the structure together. The large and small Magellanic Clouds are not points orbiting the Milky Way. They are irregular galaxies rich in gas and star formation, tens of thousands of light-years across, each one a distinct structure being slowly torn apart by tidal forces. The dozens of dwarf spheroidals scattered throughout the local group are not invisible nothings. They are galaxies, faint and diffuse, but real, each one a clump of stars held together by a dark matter halo that outweighs the visible stars by factors of 100 or more. Even the faintest ultra-faint dwarfs, the ones with only a few thousand stars, are structures occupying volumes thousands of light-years wide. They are not points, they are shapes. And the mental shift from thinking about them as points to thinking about them as shapes is what allows you to actually grasp what scale means in the universe. Here is why that shift matters. When you think about galaxies as points, as dots on a map, the numbers stop meaning anything. 2.5 million light-years is just a number. It is too large to picture. Your brain has no reference for what that distance feels like. It might as well be infinity. The number goes in one ear and out the other, leaving no trace. But when you think about galaxies as shapes, as volumes with extent and structure, the picture changes. Andromeda is not 2.5 million light-years away. Andromeda is a structure 220,000 light-years across, sitting at a distance of 2.5 million light-years. That means the gap between us and Andromeda is only about 11 times the width of Andromeda's visible disk. 11 times. That is close. That is the same as standing 11 car lengths away from another car. You would not describe that as far away. You would describe it as nearby. Andromeda is not across the universe. It is right there, hanging in the sky, close enough that its gravity is pulling on the Milky Way, close enough that the two galaxies are falling toward each other, close enough that if you could somehow watch the universe in fast forward, you would see the two structures drifting closer and closer until they finally collided and merged. The shift from distance to shape, from point to volume, turns an abstract number into something you can almost feel. The same shift applies to understanding the diversity of galaxy types in the local group. When you think about spirals, ellipticals, lenticulars, irregulars, and dwarf spheroidals as categories, as boxes you sort objects into, the categories feel arbitrary, just labels. But when you think about them as shapes, as different ways of organizing matter and energy into stable structures, the categories start to make sense. A spiral galaxy is a disk with a bulge, rotating, with spiral arms traced out by density waves, with ongoing star formation lighting up the arms in blue and ultraviolet. That is a shape. That is a structure with a specific geometry, a specific set of physical processes running inside it. An elliptical galaxy is a smooth, nearly featureless distribution of old stars arranged in a spheroidal or football-shaped blob, with no disk, no rotation, no star formation. That is a different shape, a different structure. The stars are moving in random orbits. The galaxy is red and dead. The geometry is completely different from a spiral. A lenticular is a hybrid, a disk with a bulge but no spiral arms, a structure that has the skeleton of a spiral but the complexion of a graveyard. That is another shape, another way matter can organize itself. Irregulars are chaos, asymmetric clumps of stars and gas with no coherent structure, shaped by tidal forces and interactions with larger neighbors. Dwarf spheroidals are ghosts, faint, diffuse structures dominated by dark matter, the stars so spread out that the galaxy barely qualifies as a structure at all. Each type is a distinct shape, a distinct geometry, a distinct outcome of the same underlying physics playing out under different conditions. And the conditions that produce those shapes are not random. They are the result of billions of years of interactions, mergers, gas stripping, star formation, and tidal forces. Spirals form when gas settles into a rotating disk, and density waves carve out spiral arms. Ellipticals form when two galaxies collide and the disks are destroyed, the stars mixed into a chaotic swarm. Lenticulars form when a spiral loses its gas and the spiral arms fade, leaving behind a smooth disk with no star formation. Irregulars form when tidal forces scramble a galaxy's structure, pulling it into an asymmetric shape. Dwarf spheroidals form when small galaxies lose their gas and their stars settle into a diffused configuration dominated by dark matter. Each shape tells a story. Each structure is a snapshot of a process that has been running for billions of years. And when you understand the shapes, when you picture galaxies as volumes with geometry and structure rather than points with distances, the story becomes clearer. You stop seeing a catalogue of objects sorted into categories and start seeing a population of structures evolving over time, interacting with each other, transforming from one shape into another. Dark matter is the invisible thread running through all of this. Every galaxy in the local group, from the largest spirals down to the faintest dwarf spheroidals, is wrapped in a dark matter halo. The halos are not optional, they are not minor corrections to the mass budget. They are the dominant component, outweighing all the visible stars and gas by factors of 5, 10, 100, sometimes even 1,000. The stars are just tracers, faint markers that tell you where the dark matter is. Strip away the dark matter, and the galaxies would not survive. The stars in the outer regions of spiral disks are moving too fast to stay bound without the extra gravitational pull from the dark matter halo. The dwarf spheroidals are so diffuse that the visible stars alone do not have enough mass to hold the structure together. The dark matter is what makes galaxies possible. It is the scaffolding, the invisible framework that holds everything in place. And understanding the shapes of galaxies means understanding the shapes of the dark matter halos surrounding them. The dark matter halos are not perfectly spherical, they are not smooth. Simulations show that dark matter clumps into halos with complex shapes, elongated in some directions, compressed in others, shaped by the mergers and interactions that built the galaxy over time. The visible stars sit inside the densest part of the halo, the region where the dark matter is most concentrated. The halo extends far beyond the visible stars, wrapping the galaxy in an invisible cocoon that stretches for hundreds of thousands or even millions of light years. Andromeda's dark matter halo is estimated to extend past 1,000,000 light-years from the center, far beyond the visible disk, far beyond the stellar halo. The Milky Way's dark matter halo is similar. The two halos are so large that they might already be touching, overlapping at the edges, even though the visible disks are still 2.5 million light-years apart. The collision between Andromeda and the Milky Way is not just a collision between two visible galaxies. It is a collision between two enormous dark matter halos, and the dark matter will merge long before the stars do. That invisible structure, the dark matter halos wrapping every galaxy, is one of the most important pieces of the scale story. When you picture Andromeda, you should not just picture the bright disk with its spiral arms and glowing star-forming regions. You should picture the entire structure, the disk surrounded by a stellar halo extending to 500,000 light-years, the stellar halo surrounded by a gaseous halo extending to more than 1,000,000 light-years, the gaseous halo surrounded by a dark matter halo that outweighs everything else combined and extends even farther. That is the full shape of Andromeda. That is the volume the galaxy occupies. And when you compare that shape to the Milky Way's shape, when you picture the two structures falling toward each other across a gap that is only a few times larger than the halos themselves, the scale becomes something you can almost grasp. Not fully. The numbers are still too large, but almost. You can start to see the universe not as a collection of isolated points scattered through infinite space, but as a web of overlapping structures, halos touching halos, galaxies interacting with galaxies, everything connected by gravity and dark matter into a single coherent system. The shift from points to shapes also changes how you think about your place in the universe. When galaxies are points, you are sitting on a planet orbiting a star in one of those points, and the distance between you and everything else is so large that it might as well be infinite. You are isolated, alone, a speck in an incomprehensibly vast void. But when galaxies are shapes, the picture changes. You are sitting inside one of those shapes. The Milky Way is not a point somewhere out there. It is a structure wrapped around you, a disk of stars and gas stretching 100,000 light-years from edge to edge, a stellar halo extending far beyond that, a dark matter halo wrapping the whole thing in an invisible cocoon. You are inside it, you are part of it. The stars you see in the night sky are not distant objects scattered randomly through space. They are members of the same structure you belong to, fellow travelers in a galaxy that is rotating, evolving, interacting with its neighbors, and the neighbors are not infinitely far away. Andromeda is right there, 11 disk widths away, close enough that its gravity is pulling on the Milky Way, close enough that the two galaxies are falling toward each other, close enough that in a few billion years they will collide and merge. The local group is not a sparse collection of isolated points. It is a crowded neighborhood of overlapping structures, galaxies orbiting each other, interacting with each other, slowly merging and transforming. You are not alone in the void. You are inside a shape, surrounded by other shapes, part of a system that has been evolving for billions of years and will continue evolving for billions more. That realization, the shift from isolation to connection, from points to shapes, is what makes cosmic scale feel real. The numbers are still incomprehensibly large. 2.5 million light-years is still a distance no human will ever cross. 220,000 light-years is still wider than anything you can picture in detail. But when you understand that those numbers describe shapes, volumes, structures with extent and geometry, the scale stops being abstract. It becomes something you can hold in your mind, even if you cannot fully visualize it. You can picture Andromeda as a disk twice the width of the Milky Way, wrapped in halos that extend for millions of light-years, sitting at a distance only a few times larger than the halos themselves. You can picture the local group as a web of overlapping structures, spirals and ellipticals and irregulars and dwarfs, all of them connected by gravity, all of them part of a single system. You can picture yourself inside that system, sitting on a planet orbiting a star in one of the spiral arms of the Milky Way, part of a structure that is moving, evolving, falling toward its neighbor. The universe is not empty. It is full of shapes, full of structures, full of volumes occupying space and interacting with each other. And understanding that is what turns cosmic scale from a list of incomprehensible numbers into a story you can actually follow. The diversity of galaxy types in the local group is not just a curiosity. It is a map of the different endpoints galaxies can reach, the different shapes matter can organize itself into when you give it billions of years to interact and evolve. Spirals like Andromeda and the Milky Way are the active, dynamic galaxies, still forming stars, still glowing brightly, still holding on to their gas and their structure. Ellipticals like Messier 32 are the graveyards, smooth and red and dead, galaxies that burned through their gas billions of years ago and settled into a stable configuration of old stars. Lenticulars are the faded spirals, galaxies that lost their gas but kept their disks, stuck in a transitional state between spirals and ellipticals. Irregulars like the Magellanic Clouds are the chaos, galaxies scrambled by tidal forces, rich in gas and star formation, but lacking any coherent structure. Dwarf spheroidals are the ghosts, faint diffuse structures dominated by dark matter, the smallest and faintest galaxies that can exist. Each type is a distinct outcome, a distinct shape, a distinct answer to the question of what happens when you give gravity, gas, and dark matter billions of years to play out different scenarios. And the local group contains examples of all of them, a complete zoo of galaxy types within a single small cluster. The future of the local group is not a mystery. The trajectories are known. The gravitational equations have been solved. Andromeda and the Milky Way will merge. The smaller galaxies will fall in or be ejected. The dwarf spheroidals will be torn apart and their stars scattered into the halos of the giants. In 4 or 5 billion years, the structure we see today will be gone, replaced by a single massive elliptical galaxy surrounded by a few surviving satellites and a lot of empty space. The merger will take billions of years to complete, long enough that no human civilization could ever witness the full arc. But the outcome is clear. The two giants are falling toward each other, and there is no force strong enough to stop them. Gravity does not negotiate. The collision is inevitable, and when it happens, the shapes will change, the spiral disks will be destroyed. The spiral arms will be scattered. The stars will be mixed into a chaotic swarm, their coherent rotation destroyed. What will emerge is a different shape, a smooth elliptical, red and dead, a structure with no disk, no arms, no ongoing star formation. Just a swarm of old stars orbiting a central core in random directions. The age of spirals in the local group will be over, but even knowing that, even understanding that the structure is temporary and doomed to merge, the scale of what is happening right now is staggering. 2 galaxies, each one hundreds of thousands of light years across, each one containing hundreds of billions or trillions of stars, falling toward each other across a gulf that is shrinking by billions of kilometers every year. That is not an abstraction. That is a physical process happening in real time, playing out on timescales so long that it looks like nothing is moving at all, but the motion is there, steady and patient, pulling the 2 structures closer with every passing second. And the entire process, the collision and the merger, and the transformation from spirals to elliptical, is just one chapter in a much longer story. The local group is part of the Virgo supercluster, a much larger structure containing thousands of galaxies. The local group is falling toward the Virgo cluster, pulled by its enormous mass. In hundreds of billions of years, the merged Milky Way and Andromeda, the elliptical we are calling Milkdromeda, will fall into Virgo and become part of that much larger system. The hierarchy repeats at every scale. Small structures merge into larger structures. Larger structures merge into even larger ones, and the process has been running for more than 13 billion years, since the first galaxies formed in the early universe, and it will continue for trillions of years into the future. The awe-inspiring part is not just the scale. It is the fact that we figured it out. A species that has existed for only a few 100,000 years, living on a planet that has been around for only 4.5 billion years, orbiting a star that is only one of hundreds of billions in a galaxy that is only one of trillions in the observable universe, managed to map the shapes of galaxies millions of light years away, measure their distances, calculate their masses, trace their motions, and predict their futures. We built telescopes sensitive enough to detect light from galaxies so faint they are barely distinguishable from noise. We developed techniques to measure the velocities of individual stars in galaxies millions of light years away. We mapped the distribution of dark matter by studying how galaxies rotate and how their gravity bends light. We figured out that the universe is expanding, that galaxies are moving away from each other, but that on small scales gravity wins and clusters like the local group stay bound together. We predicted the collision between Andromeda and the Milky Way billions of years before it will happen, based on nothing but observations of how fast the galaxies are moving and the laws of physics that govern their motion. That is not a small achievement. That is one of the most remarkable things a species has ever done. And the work is not finished. The census of the local group is still incomplete. New dwarf galaxies are being discovered every few years as sky surveys get deeper. The exact masses of Andromeda and the Milky Way are still uncertain. The fate of Triangulum is still being debated. The properties of dark matter, the invisible substance that holds galaxies together, are still not fully understood. The details of how galaxies form, how they evolve, how they interact, are still being worked out through observations and simulations. The story of the local group is not done. It is still being written, one observation at a time, one galaxy at a time, one measurement at a time. And every new piece of data, every new discovery, adds another layer to the picture, another detail to the shapes we are mapping, another clue to understanding how the universe works. The shift from thinking about galaxies as points to thinking about them as shapes is not just a technical adjustment, it is a conceptual revolution. It changes how you picture the universe. It changes how you understand scale. It changes how you see your place in the cosmos. You are not sitting on a speck orbiting a speck in an infinite void. You are sitting inside a structure, a galaxy with a disk and a halo and a dark matter envelope, part of a system of galaxies bound together by gravity, all of them interacting, all of them evolving, all of them heading toward a future that is already written in the trajectories and the math. The universe is not empty, it is full of shapes, full of structures, full of volumes occupying space and moving through time. And understanding that is what makes cosmic scale something more than a list of incomprehensible numbers. It makes it a story. A story about how matter organizes itself into galaxies, how galaxies organize themselves into clusters, how clusters organize themselves into superclusters, and how all of it, every structure at every scale, is connected by gravity and dark matter into a single coherent web. That is the true scale of the universe, not the distances, the shapes. And once you see the shapes, once you understand that galaxies are volumes and not points, the universe stops being an abstract collection of numbers and becomes something you can almost hold in your mind. Almost. The scale is still incomprehensible. The distances are still too large, but almost, and almost is close enough. So here is where we are, sitting on a planet orbiting a star in the outer regions of a spiral galaxy, containing somewhere between 200 and 400 billion other stars. That galaxy, the Milky Way, is not sitting alone in empty space. It is part of a family. A gravitationally bound cluster of roughly 80 to 130 galaxies, most of them so faint you could stare directly at them and see nothing, scattered across a volume 10 million light-years wide. We call it the local group, and it is ours, our neighborhood, our corner of the universe. The two largest members, Andromeda and the Milky Way, dominate everything. They are falling toward each other at 110 kilometers per second, closing a gap that has been shrinking for billions of years and will continue shrinking until the collision happens in roughly 4.5 billion years. When it does, the spiral arms will be destroyed. The disks will be scrambled. The structure we see today will be gone, replaced by a single massive elliptical galaxy, smooth and red and dead. The future is not uncertain. It is written into the trajectories and the math. Gravity does not negotiate, but the remarkable thing is not the scale. It is not the distances or the masses or the time scales. The remarkable thing is that we figured it out. A species that has been looking up for only a few thousand years managed to map the shapes of galaxies millions of light years away, measure their motions, calculate their masses, and predict their futures. We learned to see past the faint smudges in the night sky and recognize them for what they actually are. Not points, not symbols, shapes, volumes. Structures hundreds of thousands of light years across, wrapped in invisible dark matter halos, interacting with each other, evolving over billions of years, part of a system that has been running since the first galaxies formed and will continue running long after the last star dies. You are not sitting on a speck in an infinite void. You are inside a structure, part of a galaxy, part of a cluster, part of a web that stretches across the entire observable universe. And every time you look up, every time you see that faint smudge of light in Andromeda, you are seeing one of the closest neighbors we have. Not a distant abstraction, a neighbor, right there, close enough that its gravity is pulling on us, close enough that we are falling toward it, close enough that in a few billion years the two galaxies will collide and become one. Until then, look toward that fragile oval and remember that every faint companion around it carries another surviving chapter of our neighborhood's unfinished story.